by just plugging Solomonoff into the sequential decision theory framework, sounds like an optimal decision maker in arbitrary unknown worlds. And if you parse this sentence, this feels like AGI. The whole conversation by Marvin Minsky was, and I'm paraphrasing, I don't know exactly, but pretty much, Solomonoff's theory is a beautiful theory about prediction. Everyone should know everything about this theory and spend the rest of their lives working on it.
Welcome, everyone, to the Cartesian Cafe. I am your host, Tim Nguyen. Today, we're very lucky to have Marcus Hutter here with us. Marcus is an artificial intelligence researcher who is both a senior researcher at Google DeepMind and an honorary professor in the Research School of Computer Science at Australian National University. He is responsible for the development of the theory of universal artificial intelligence, for which he has written 2 books, one back in 2005 and one coming right off the press as we speak. Marcus is also the creator of the Hutter Prize, for which you can win a sizable fortune for achieving state-of-the-art lossless compression of Wikipedia text. Welcome, Marcus. How are you doing today?
Hi, Tim. I'm fine. Thanks.
Yeah, great. I'm glad I'm finally able to interview one of my colleagues at Google DeepMind. Of course, it goes without saying that everything we discuss is reflective of our own thoughts and opinions and not those of our employers. That being said, before we dive into the details of what will be a very fascinating topic, why don't we talk a little bit about your background? You apparently started out in life as a physicist and then transitioned to computer science and AI. Maybe can you say a few words about why and how that happened?
Yeah, it's actually a little bit more complicated. At some point in my life, I realized I was born already as a Bayesian, but I mean, we don't have to really dig into this. I always had discussions with other people, and before I knew about frequentists and Bayesians, and then later I realized, okay, most of people are frequentists because I mean they learned that at university, and I'm Bayesian. So I always say, no, I'm born a Bayesian. But no, my interests from a very young age were twofold. One was understanding the universe, which naturally leads to want to study physics. And the other one is creating AI. So I toggled back and forth between, so I did the German equivalent of a bachelor's in computer science, then a bachelor in physics, then a master's in computer science, then a PhD in theoretical particle physics. Then I had a 4.5-year stint in the industry. But then I really wanted to return to do fundamental research, and sort of then since the year 2000, I finally settled to working on AI.
Okay. All right, great. Maybe one more question. What's the backstory behind your Hutter Prize? Why did you create it? Why do you care about it? And how did you secure the funds for it?
Okay. So the reason is, and essentially one reason, yeah, but sort of has multiple facets. As we will discuss in this podcast, there is a close relation between being able to compress data and being able to predict data. Actually, the prediction compression relation is in a sense perfect, right? There is no difference between prediction and compression. And being able to predict well is at least, I would say, half the rent for a general intelligent agent. So if you want to behave well in an uncertain world, you need to make predictions and then make plans and decisions accordingly. And if your predictions are bad, then even if your decision algorithm is good, your actions will be bad. So this connection is pretty obvious for a set of people who work on compression. Stochastic compression is peculiar, and it's now, meanwhile, since we have the large language models and they're trained on log loss, so this duality between compression and prediction now is becoming mainstream. But when I started the Compression Prize, that was not so well known, and I wanted to advertise that. But apart from advertising, I also want to solve the AI problem. And since prediction is one half of it, we need better predictors, which means better compressors. So I thought I want to encourage people to come up with better compressors because that is closely related to then prediction and AI. And as we will discuss briefly, probably, these LLMs are essentially, the models. The better they compress, the better they perform on downstream tasks. And with the series of funds, I made a big gamble. I mean, initially it was only nominally 50,000 euro, but you don't get the 50,000 euro in one go. If you beat the current state of the art by X%, you get X% of the price. And my reasoning was, either progress is slow, which I expected, and then I can afford to pay it out, or progress is sudden, then this is such a major event that I'm willing sort of, to scrape somehow the funds. Meanwhile, it's 500,000 euro nominally, but usually the improvements are, a couple of percent, every couple of years. So I only have to pay out, smaller amounts. If suddenly somebody compresses to half size, then I have to take another mortgage on my house.
Okay.
But I will definitely honor my commitment. So don't worry about that. I'm so far.
All right. I hope you'll get a flood of participants after our conversation. Thank you, Marcus. Before we dive into the details, why don't we get an overview from you about the theory of universal artificial intelligence? You're responsible for its creation. Can you say a few words at a high level what it is and why people should care about it?
Sure. Yeah. So, okay, let me go back a little bit. As I said, I couldn't decide between physics and AI. Physics had beautiful math and elegant theories and so on, while on the other hand, I believe that AGI now has more impact, more practical impact. But at the time, at least in the 90s when I studied it, AI wasn't really, the field wasn't really too attractive to me. So that there was good old-fashioned AI with logical reasoning expert system, which was sort of reasonably formal. But I never believed that this is the way to true AGI. And then there were, of course, neural networks, but I didn't like the neural networks too much. They work to some extent, but also not very well. And anyway, and I didn't have any good ideas myself. So I left the field, worked for 4.5 years in a startup. But after a while, after a couple of years, I couldn't stop thinking again about AI. And finally, more or less, in an instant, I realized what has to be done and what was missing. To keep it short, many fields start out in an informal way, and then they get more and more formal, which helps sort of with the technical and the scientific development. I think about physics, the energy was a mysterious concept, and these kinds of things that now it's rigorously formal. But if you look at AI, nobody has really formally defined what intelligence is. But AI is about artificial intelligence. How can we work about AI if we don't know what it is? You can do it, but I thought it will be extremely useful to know what is actually the ultimate goal. And I knew, for instance, if you play chess and we play minimax to the end of the game, that is a theoretical optimal thing to do, right? So for perfectly well-specified environments, we know how to do this sequential decision in an optimal way. But the world is unknown and uncertain, and we have to do predictions. And I wasn't aware at that time neither about Kolmogorov complexity nor Solomonoff induction, but then I realized generalization via Kolmogorov complexity and Solomonoff, which is sort of rediscovered, but way 2 decades too late, is the way to go. And so what I discovered is, or rediscovered is, that you can make predictions of arbitrary time series, whether it is stock market data, weather forecasting, or number sequences 1, 2, 3, 4, 5, or any data. You can do that in a certain sense, in an optimal way, without knowing the underlying structure of the problem, using what has been known even at the time, as Solomonoff induction, using Kolmogorov complexity. But that is only prediction. right? And agents also act. But I knew sequential decision which solves the action problem if you know the environment. And in hindsight, I put these things two together and arrived at a model which does optimal decisions in arbitrary unknown worlds. And if you think about this sentence, right, this is what AGI is or should be about. And that's what I coined universal AI, wrote down the mathematics, and in the last 25 years, proved a lot of theorems about it. And we also approximated to some extent and implemented it. And so there's now even, nice connections to actually large language models. And we probably a little bit talk about this. If there's somebody here listening who primarily or only cares about large language models. So they will be covered too.
Okay, great. All right, great. That's a lot to unpack. So I think probably the best way forward is let's just start writing a technical outline, because I think once we start getting into the details, more of this will become clear. So let's now go to the whiteboard, and I'll start with writing a list of topics that I think we'll be covering and following, and of course we'll adjust along the way. So the first kind of phenomenon we'll be discussing is what's called universal prediction, which is what you alluded to before. And without loss of generality, what is the problem of universal prediction? Basically, we're given a sequence of zeros and ones. In general, it could be an arbitrary alphabet, but binary is sufficient to illustrate the point. We want to predict probability of next digit, right? So that's the prediction problem, and it's universal in that we a priori there could be any probability distribution governing the sequence of zeros and ones, and our job is to sort of discover that, so to speak, right? And so this is the universal prediction problem. If I see a stream of binary digits, can I use that sequence of observations to guide my prediction for the next digit that I see, right? And the way we're going to kind of go about explaining how to solve this problem will be through a few steps. The first thing we could do is start with the warm-up, which is to explain Laplace's rule of succession. So this is one of these, I guess you could think of it as a simple guideline of how to make the next prediction given the observations, but of course there's a mathematical basis for this, and we'll go into that. And from that warm-up, which I think will be a very nice illustrative example to get people familiar with the problem if they haven't seen it before, the right framework, or the more general framework for this is Bayesian sequence prediction. So sort of Bayesian reasoning underlies all of this, and I guess maybe that's not a surprise given you said that you were born a Bayesian, but of course, you start with the prior, you make some observations, you update your beliefs, and just keep iterating on that, and we'll see how that also, how Laplace's rule is an instantiation of that. And sort of that sets the stage for talking about Kolmogorov complexity. Kolmogorov complexity, which philosophically, when we combine it with Bayesian reasoning, is a form of Occam's razor, as we'll see, right? Because Occam's razor is about keeping your hypotheses as simple as possible, and Kolmogorov complexity is a way of measuring complexity, and so we'll see how those two things are related and tie that into Bayesian reasoning. And you already mentioned Solomonoff induction, so that will sort of be the highlight of this section, which is a way of combining Kolmogorov complexity with Bayesian sequence prediction. And in some sense, this basically gives us a way of solving the universal prediction problem, right? That's what sort of Solomonoff induction does. So this is basically a very rapid overview of the first part, universal prediction, and then sort of.
Can I add two things?
Of course, sure.
So here I would like to mention a few special model classes, which are bigger than just predicting sort of IID sequences, but small enough so that you can do that efficiently. The names will come later. And then after this, probably It's discuss loss functions.
Sure, of course.
Because it somewhat ties into the next section where we then deal with value functions, and loss is sort of more or less the same as value functions.
Sure. Right. Yep, that makes a lot of sense. Of course, we want to get to universal AI. So how do we get to there? So that brings in the second section, which is we'll talk about universal agents. And by agent, that basically means we're going to combine prediction from the previous section with planning, right? Because agents act. And so if you have a model of your environment and you want to say optimize your reward, then that gives you a way of planning, right? And what we'll find is that when we kind of combine the ideas from the universal prediction side with action and try to get something that's optimal, we get a universal optimal agent, which has this nice acronym, AIXI, Artificial Intelligence Cross Induction, right? Maybe just to clarify that when we talk about why do we keep using the word universal? Universal because we don't care what the environment, or how to say, the environment can be arbitrary, just like the generative distribution for our sequence of zeros and ones in section 1 is also arbitrary, and so we want a solution that works for arbitrary or general situations, right? So that's the
yes. And before we get to that, I have to first introduce agents in known environment. Agents.
That's right.
Known environment.
Okay, great. And then after we discuss those two, we'll just see what we have time for in terms of extra material, right? So there's a lot we can cover. Your books have lots of material, but just to list a few that we might cover, just depending on how much time we have. We can talk about, say, computable approximations to all of this, because for those who know, Kolmogorov complexity is not a computable function in the Turing machine theoretic sense. So of course, this is nice theory, but if you don't have something that's computable, maybe it might be limited, and so you want to come up with computable approximations. So that's something we may want to discuss. There's also maybe multi-agent settings where there's more than one actor, right? And maybe
this is definitely the multi-agent. We should definitely cover multi-agent.
Okay.
I mean, we can be very brief about it. So it's
sure.
Anyway. I mean, this is related to the grain of truth problem. It's too great not to mention it.
Sure. Okay. And then finally, of course, any philosophical discussions about AI that might arise from these both technical and philosophical considerations that we're discussing here. Okay, so this sounds like a pretty good outline.
Yeah, maybe we should add for the people who are here for the language models that I will also talk a little bit about LLMs, but don't expect too much.
Okay.
But we have one recent paper which really ties it nicely together, the Solomonoff Induction and the LLMs.
Sure. Okay, great. All right. So why don't we go to the next page, and why don't you start us off with describing to us Laplace's rule?
Let's start with something super simple. Well, maybe just start with even simpler, frequentist predictions. I mean, we need a notation in this setting anyway. So we have a sequence, x1, x2, x3, and so on. And for simplicity, we assume most of the time binary, but everything can be extended to finite alphabet more or less straightforwardly. And to larger alphabets, that's usually I leave to the mathematician, because I think it's AGI irrelevant. It can be mathematically, of course, interesting. Okay, so I also use everywhere the abbreviation x1 to n, which is just the sequence x1 up to xn. Okay, so let's assume they are drawn IID, so from a Bernoulli theta process, right? And theta is in 0, 1, so that's a biased coin. If theta is not equal to half, it's equal to half, it's a fair coin. And we want to, I mean, most of the time in statistics, you want to do induction, you want to infer the unknown parameter, right? And, well, how do we do that? Well, we count the number of ones. In binary, I can just take the sum. Wait a second. So assume we have seen k once, and then n minus k. N minus k is, of course, the number of time steps where xt is equal to 0. Just a complement, of course. Okay. And the naive frequency estimate would just estimate theta as k divided by n. And from the law of large numbers, we know that it converges to, let's call it theta 0, if the sequence is sampled from, well, IID from p theta 0. Okay. So long, so good. Most of the time, I will be concerned directly with prediction rather than parameter estimation, which has the advantage is that sometimes the parameter estimation can be harder than the prediction. For instance, if you cannot uniquely, if you have a model class, you cannot uniquely identify the parameter, you may still be able to do prediction well. So it avoids a lot of complications in more complicated classes. Here, in the simple Bernoulli class, there is no difference. So the probability under parameter theta that the next symbol is 1, given the history, right? This is just theta. So the predictive distribution is the same as the parameter. So it's the same. Okay. So why is this bad? Okay. And this is where Laplace sort of comes in. So he considered the problem of the sun rising. So he was at a certain age, I don't know how old, I don't know, maybe 30 years old. And so that means he has seen the sun maybe rising 10,000 times. And he asked about what is the probability that the sun will rise tomorrow again. I think he had another estimate where he estimated that the world had been 4,000 years old, according to the Bible. And so maybe around 1 million days. Yeah. So you have even more data that the sun rose every day. So what's the probability of the sunrise tomorrow? Okay. Let's look at the data sequence, the sequence x1 up to, x, say 1 million. Yeah. They're all ones. Okay. So k is the same as n. So we take the frequency estimate, k divided by n, which is just 1. So we would predict that the probability the sun will rise tomorrow is identically 1. So we are absolutely sure that the sun will rise tomorrow. And that feels, of course, way too overconfident. And he asked, how can we come up with a prediction which is more reasonable? So it should be something close to 1, but not exactly 1. And so let's derive Laplace rule. I present you the end result. The end result first was that he says we should predict this probability.
By the way, notation-wise, 1 to the million means a concatenation of 1 million ones. Is that right? Your
Yeah.
Okay, not literal exponentiation. Okay,
The upper exponent has often multiple meanings. Yeah,
I see. Okay. I originally tried to correct it as plus because I thought you were looking at numbers, but I realize now it's just concatenation. So let me fix the whiteboard now. Okay, good. So, and he said instead of using k divided by n, use k plus 1 divided by n plus 2. And if you plug in k to be equal n, that would be n plus 1 divided by n plus 2, which is 1 minus 1 over n plus 2. So if you assume the sun rose 1 million times, he would say the probability the sun rising tomorrow is roughly, not rising tomorrow is roughly 1 over 1 million. And at least that's not implausible, right? The probability cannot be much higher, right? If the probability of sun, and we remember that was at a time where people had no idea about the sun being a fusion reactor and exploding at some point at a supernova and these kinds of things. So this IID model was at least not totally absurd. Let's phrase it that way. And it cannot be much larger than 1 million, because if the sun would rise, or fail to rise, more often, we would have seen it already. So it is sort of a lower upper bound, depending how you view it. But maybe it could be even closer to 1, and you could argue about it.
But now let me give you the derivation. And that's really beautiful, and I think everyone should know this. I mean, it is really one of the most basic applications of Bayesian inference and the most beautiful one. So we don't know this parameter theta. And well, frequentists deal with this in their own way. But the Bayesian just says, okay, we have an uncertainty over this prior theta. And we also model this by a probability. This is not a sampling probability, but this is objective belief probability or epistemic probability, okay? Usually I use the letter W, but you can also use P or whatever you like. And the indifference principle tells us if we don't know anything, we should assume a uniform. Theta is continuous parameter in the interval 0, 1. So a uniform prior would be just equal to 1. Okay.
Actually, let's just back up for a second, because I don't know if you've already kind of alluded to what you said, but I think one thing that might be puzzling about this, if you haven't thought about it before, is if like what's wrong with assigning probability equal to 1, right? Because I've seen it a million times before rising, and so if I were just to obviously use the sample estimate, then of course. For all past observations, the sun always rose. So I should just kind of duplicate that estimate, right? Like what's wrong with that?
Okay, first give you an example more close to home, right? I have a coin, right, which could be a fair coin or it could be a coin which has 2 heads, okay? I flip it 10 times, right? Let's say 10 times, and it always comes up head. Are you 100% certain that the next time is head?
That's right. Fair enough. There's still a small chance. Right now, you could have had a coin that had 2 heads on it, or you could have just gotten very lucky with a fair coin, right? So
exactly. Yeah. So in this case, of course, the probability is 2 to the minus 10, right? So the probability of it being the fair coin is very small, but maybe let's put in the mix a coin which is heavily biased towards head, right? You know, has a 90% probability of head, right? And now you see 10 heads. Well, there's actually, I don't know the numbers now, maybe there's a 50-50 chance it's a 90% head coin or the full head. So you should always reserve, especially if you allow more complex models, the probability that something. So that is actually a general principle. Everything which is not logically excluded, right, or by physical laws, but even physical laws may not be 100% certain, right? You should assign a non-zero probability to it, right? So to the event that the sun will not rise, yeah, it can happen, right? Why not, right? So you should assign at least a non-zero probability, and frequentists would assign a 0 probability. So they're just overconfident. You can view it from a betting perspective, right? The Dutch Punkt argument. How much would you bet, right? Against or towards the sun will rise or not? Of course, I would easily bet 100 to 1 that it rises tomorrow, right? 1,000 to 1, but I wouldn't bet sort of 1 billion to 1 or whatever, right? Maybe because I mean, with sunrise, maybe then we are all dead, right? So we need maybe coding or something like this. Anyway, never assign probability 0 except to logically inconsistent events.
Sure.
The anti-event.
Okay, great. Yeah, and I think that's now a good segue into talking about this assigning a prior, because that's exactly, therefore, assigning weight to all candidate hypotheses that aren't ruled out by the data.
Exactly. So if we had just 2 hypotheses, right, fair coin or always head, it would be just, a priori we have no idea. We would say with 50% it's always head coin, and with 50% it's a fair coin, and then deal with it. But let's assume here, we have no idea about this bias of the coin, so take a uniform priori.
Okay, sure.
So now, before we continue, let me maybe present you Bayes' rule in the general form. You can present it in many forms. The most useful form is the following. Let's assume you have a class of hypotheses, hi, I equal 1 to k or so. What does it mean? So these are point hypotheses, and they're mutually exclusive. So here what we mean is that the probability of your data, x1 to n, under some hypothesis I has a certain probability distribution. So for instance, H0 could be fair coin, right? Then this would be just 1/2 to the n. H1 could be all heads. Then for the sequence all ones, that would just be 1, right? So this is just the hypothesis is just a probability distribution. We only care about sequences here over sequences here. Okay. Then we have a prior, or maybe at this stage I use the P so that it's more conventional over the hypothesis. So if we had sort of fair coin versus head coin, right, it would be 50/50 or something like this. And I ask, what is my posterior? That's my prior belief. What is my posterior belief in this hypothesis after I have seen data? Okay. And Bayes' rule says you should take your data, the likelihood function, and you multiply it with the prior, and then you need to normalize it so that it's a proper probability distribution. And this normalizer, let's call that P of x1 to n, is just the marginal distribution over all this hypothesis. So that is called the Bayesian evidence, or the marginal distribution. Has many names. Partition function. Okay, and I mean, if you flip it around.
Sorry, just interrupt. I think.
Sorry, on the left-hand side, I missed something else. That's a posterior here, of course.
Yes, that's right. I was going to say that. Yeah.
It's x1 to n. So if you flip this, if you flip the denominator to the left-hand side, you see it's just P of h given x is P of times P of x is P of x given h times P of h, which is just the definition of conditional probability. So there's really not much to it, okay? But so that's the great thing. If you're Bayesian, that's essentially the only thing you need to know. And you just always, you think about your prior, you come up with a model class, and then you just, crank Bayes' rule.
Right. So maybe just to say this in a few words, right? You start with some, your prior is your set of initial credences as to how likely the individual hypotheses are. In this case, there's a hypothesis for each value of the probability that the coin produces a 1, right? So each HI is the theta, and then the likelihood is just a computation how likely the data is given that value of theta, and the posterior is saying, well, what is my new belief in the value of the theta's condition on the observation I just made, and that basically by the rules of probability theory, this is what Bayes' rule tells you how you should update your probabilities.
Exactly. Yeah. So now let's instantiate it. So this is completely general. Whatever your model, and there's no IID assumptions or something, or stationarity or Markov or something. So that is completely general. But let's go back to the Bayes to the Laplace example. So here, the class, we have not a class of finitely or countably many hypotheses, but continuum. So the only thing which changes is that the sum is replaced by an integral. Okay. And the hypothesis class is now, H theta or just theta with theta in 0, 1. Okay. Then my likelihood function onto n under h theta, or just abbreviate theta, is, okay, so let's assume there are k ones as before and n minus k zeros, okay? So it's an IID model. So this is just the product over all p of x t equal 1 to n, okay? What is the probability over 1? Well, the probability of 1 is theta. And how many ones are in this sequence? Okay, k. And the probability of 0 is 1 minus theta, and there are n minus k zeros in the sequence. So that is my model of a biased coin. Okay. And now the prior, as before, it's up here. Okay. So now we compute the posterior. Before we compute the posterior, we have to compute the denominator, which is always the hardest part. Sometimes it's impossible, and there are all kinds of very sophisticated tricks to still compute the posterior without the normalizing constant. And here it is very easy to do. Roughly speaking, it's also a rule of thumb. If you can compute the denominator, you can compute all other quantities of interest usually easily. So that's a rule of thumb. And we will see we can actually avoid even looking at the denominator. So now let's compute the marginal distribution, so the denominator. That is, as according to this formula, is integral over the likelihood times the prior, so that is just in this different. So that is integral 0 to 1, theta to the k, 1 minus theta to the n minus k, d theta.
So just one question. This is the likelihood, right? In the integrand.
Yeah, the integrand, that is a likelihood times the prior, yes.
Yeah. So I just wanted to reflect that in the notation just to be pedantic here.
Yeah, that is the same as p of x given h theta.
Yeah, so this should be a conditional on theta, I guess. Yeah.
Yeah, I mean, I have to put so you can compute this integral, and this, so and this is the beta function, which is k of k plus 1 and n minus k plus 1. And the beta function is just a product and ratio of 3 gamma functions, but let's just skip over this. Yeah, so that closed form essentially. Okay, and the gamma function for integer values is, of course, just factorials. Okay, so now we can compute the posterior e of theta given x 1 to n, right? Which is just, I mean, I can write it. Well, okay, let me write it out. So that is a likelihood function, theta to the n 1 minus theta to the n minus k, times the prior, which is 1, divided by this beta function, which is a constant. Okay. By the way, I will later sometimes just use this notation with a cross over the equal, which means apart from a constant. Okay. Okay. So the posterior is also this expression, and if you look now, so if you here you have a parameter theta, which is between 0 and 1, and you ask about the posterior distribution. So before we have seen any data, so for n equal to 0, well, this is just the prior, and we are not sure what the theta is, so it's just this uniform distribution. But now, once we have seen a lot of data, and assume it was a fair coin, then k is about n half. And then if you look at this expression, it would look like this, a little bit like a Gaussian. So the probability concentrates around, well, 1/2 if it's a fair coin, and around theta 0, you can easily show that if it's a coin with bias theta 0. And the width is around of the order of 1 over square root of n. So, and then, this converges to the point estimate, as we all expect. Okay. But okay, this gives you the posterior, but Laplace asked about the predictive distribution. Okay, so he asked about what is the probability of x, the next symbol, given x1 to n. Okay, and there are 2 ways of computing this. So the standard way is we compute the posterior. Then I should start it differently. So I ask, what is the probability of xn plus 1 given theta? So if I know theta, what is the probability of next bit being 1? Okay, being 1 is 1, and being 0 is 1 minus theta. Okay, but I do not know theta, but I know I have a belief over theta. So I multiply this with my posterior belief over theta and integrate over this. Okay, this gives me the conditional distribution, and it is very easy to see that this is simply p of x1 to up to n plus 1 divided by p of x1 to n. So I could now do this, look at the posterior, plug it in. This is just the binomial, multiply with another theta, integrate it out, blah, blah, blah. But it is much easier to use this expression because, I mean, if you look at the conditional distribution P of x given, the history, well, by definition, it is just P of x1 up to n plus 1 divided by P of x n plus 1. Okay? And the denominator we have just computed above, right? This is this beta function, beta of k plus 1 and n minus k plus 1. And what is the numerator? Okay, let's ask what is the probability of the next bit being 1, okay? So we now look at the sequence, which is x up to xn, and then we have a 1, so the next bit is 1. So k, which counts the number of ones, is 1 more, okay? So the numerator is exactly the same formula, but k has increased by 1, so it's k plus 2 n minus k plus 1, okay? If you now plug in, the beta is 3 gammas, and the gammas are factorials, and everything cancels out, and as an end result, you get k plus 1 divided by n plus 2, and that is Laplace rule, which is very beautiful. Okay, so let me add one tiny thing. So okay. Laplace assumed a uniform prior, and I don't want to go into details. There is reasons for choosing a prior which is slightly more heavy on the tails. That would be a beta 1/2 prior if somebody cares. I can write it down, but it's not really important. And this is called then the KT estimator. Maybe that's important, the KT estimator. And if you use this prior, then instead of k plus 1 divided by k plus 2, you get k plus 1/2 divided by k plus 1. Very similar, and sort of that is the modern version.
You mean n plus 1?
n plus 1 in the denominator, yeah. n plus 1. Yeah, which gives a very similar result.
Actually, okay. Can you say a little, this is something I actually don't know. Why would you have, I guess there's some optimality with this prior. So this prior is going to look something more like, as you said, it's going to be. Yeah,
so there are right. At least 2 different arguments for it. Yes, it will look like this. So it's proportional to theta to the minus 1/2, 1 minus theta to the minus 1/2. So it actually goes to infinity.
Yeah, sorry. Okay.
At the end. And so there is 2 arguments. One argument is, so the uniformity principle says that if you don't know anything, you'll assume a uniform prior. But should I assign this uniform prior over the parameter theta? Or I can reparameterize my problem, assume instead of using the parameter theta, I use the parameter psi, which is theta square, which is also in 0, 1, right? And say, I just parameterize it this way. I should use a uniform prior over psi. But then it's a non-uniform because, of the formula how to transform densities. So this uniformity principle, if you apply it naively, is not so-called reparametrization invariant, which is bad, right? And the Jeffreys prior, okay, if we want to go there, uses the following: uses the square root of the determinant of the Fisher information matrix. But let's move on, right? Whatever that is, right? If you use this as a principle for assigning your prior, which is a little bit weird at the beginning, but it's actually has information geometrically has a lot of meaning. Then, if you do a reparameterization, you still get the same prior. So if you start with psi and compute the determinant of the Fisher information matrix with psi, then you get the appropriately transformed prior. The other justification is if you look at redundancy bounds or regret bounds, and you want them to be sort of minimax optimal, then this KT prior comes out of this.
Okay, I like the first reason, because you don't need to prove a theorem or know something sophisticated. It's just it's an a priori sensible thing to have reparameterization invariance.
Yes. So people want to look it up, then out of the prior.
Sure. Okay.
They are the same, but with the different justifications.
Yeah.
So next, maybe we go to the general case of sequence prediction, right? We essentially already have everything. Yeah? There's not really much extra to do. So now we start with a model class M, which contains distributions, right? Before it was, H index nu or something like this. So nu of, maybe notation becomes a little bit more compact, right? So x1 to n is some probability distribution over sequences, okay? And I have a class of these distributions. And from now on, with some exceptions, I will assume that this class is, I have to write it differently, is countable, M is countable. Most of the time, so that I don't have to deal with integrals. And I take a prior over this class, and then I compute the Bayesian mixture distribution or evidence or partition function or whatever you want to call it. Xi1 to n is the same as before. Some likelihood times prior nu in M. And then I do predictions now also for notational convenience, I predict xt given up to t minus 1. So another x less t is x1 up to x1. Okay.
So let's just back up a little bit. Okay, so a lot of notation was written here. So first of all, M is our hypothesis space, essentially.
Yes.
In the previous example, it was actually not a countable space. It was the unit interval, because we had a hypothesis for every coin flip probability of equal to 1. Now we're going to simplify to countable, because ultimately we want to get to a regime where we want to say implement this on a computer, and of course the set of programs is countable. So that's kind of the restriction looking ahead, why we want to consider things that are countable, correct?
Exactly. I mean, if it's uncountable, then you just replace that as the sum by an integral as before, and the prior is a prior density. But I don't want to constantly deal with the two cases.
Sure.
And the countable case.
Sure. And of course, and I think maybe just one step for clarity before we start start evaluating these quantities on actual sequences. Really, your prior is without writing. Again, it's evaluation inputs. You're saying my prior, which you wrote as C here, is say some weighted sum. I think in your book you used maybe a subscript.
Yeah, you always use the word prior. Solomonoff used the word a priori distribution. But let's not even call it a priori. I mean, if you want to call it a priori distribution, the prior is W of nu. That's the prior, and the Xi is. Call it Bayesian mixture, call it Solomonoff distribution later, call it universal distribution, call it Bayesian mixture, call it Bayesian evidence, call it partition function. Don't call Xi prior.
So just to make our terminology consistent, so W is the prior and C is this mixture over the measures in M with respect to that prior.
Yes.
Okay, great. Okay, I'm happy with that terminology. Okay. Okay, and maybe one more comment. So you start with this mixture, and the formula you just wrote here, well, it's just the evaluation of that mixture on a sequence of length n, but what you were about to write is how you're going to update that mixture using Bayes' rule, essentially. I'm not sure that's the best way to say it, but yeah.
Actually, I mean, you would update the prior to a posterior, right?
Mm-hmm.
But as I said, I want to skip the posterior and directly consider the predictive distribution.
Yeah, I see what you're saying.
And there is no real update. Sort of Bayes does all this under the hood, right?
Yep.
So it is just, you have your mixture distribution and you take the ratio of Xi of, so again, let me write it down, Xi of x1 up to t divided by Xi of x less than t. And you could write it as an integral over, posteriors and like blah, 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 and so on. But, this is all gone now. From now on, I only consider predictive distributions. Maybe at some point the posterior will pop up again. But mostly I'm interested in prediction and not induction.
Yes, I see. Basically, yeah, I mean, this kind of came up also in our Laplace example. You could keep track of the intermediate quantities in terms of the prior and the iterated posteriors, but that all gets absorbed into under the hood, as you said, when at the end of the day, if all you care about are these predictive distributions, that's implicit in everything, but you never need to explicitly kind of keep track of it. But it's there if you wanted to recover it.
Exactly. Yes.
Yeah. Okay. Great.
Okay, good. So now we have this predictive distribution. And so before, in our very simple model class, we showed that this converges, or this predictive distribution was Laplace rule, k plus 1 divided by n plus 2, which converges, of course, like frequent is asymptotically to the true parameter theta 0. Okay. Now we have made no assumptions about this news, about this probability distribution. So one could be, for instance, a distribution which is 1 on the digits of pi, right, and 0 on all others. So it's a deterministic environment which produces the digits of pi, right? And there's no statisticity. Or it could be 0, 1, 2 zeros, 1, 4 zeros, 1 or something. So anything you want. So there is no notion of convergence to a parameter anymore. There is a sort of parameter underlying the nu. We could talk about it. But as I said, I don't want to. But we consider the predictive distribution. So we can still ask questions like, assume the data x1 to infinity is sampled from the distribution mu, and the true distribution I call always mu. Before it was theta 0. Theta 0 is usually the true parameter. And here mu is always the true thing. And let's assume it's in the model class M. Okay. So if we know mu, so x is sampled from mu, we cannot, if it's stochastic, we cannot deterministically predict bits like in a coin flip, right? But we could ask, what is the true probability of the next bit given the history, okay? In the Bernoulli example, that would be theta 0, okay? But we don't know mu, so let's use the Bayesian predictive distribution xi for prediction. Let's use this one instead, because this we can, in principle, compute, okay? And now we can ask, how close is this to the truth, okay? So let's take a square. And so it would be nice, if we somehow could converge, prove that it converges to 0. Well, of course, it will not converge to 0 on all sequences, only on sequences which are sampled. So maybe almost surely.
Maybe let's just say a few words, because if you haven't seen this before, it's maybe a little bit abstract. So mu is this true probability distribution of the sequences you observe. You don't know what it is. What you do have is this mixture where you decided what the weights were in advance. Is there a, how do I say, playing devil's advocate here, is there a way to, why should I expect the C to converge to mu?
Well, okay, I can give you some intuition. I could even present a proof, but I want to move on, or maybe at least some steps of the proof. So first, let me write down the result you can prove. Okay, so you can prove this result, and I'll come back to it in a second. But you can prove something much stronger, and the way actually you prove this convergence result is via the stronger result. That's the reason why I want to present the stronger result. Okay, so you cannot, in the IID case, we could prove a rate, right? So the psi deviates from theta 0, and the rate is sort of 1 over square root of n or whatever, right? But in the general case, you cannot prove a rate in this sense anymore. But what we can do is, okay, first we take the difference squared, then we sum over all time instances up to infinity. So we take all the deviations and sum over it, okay? And then we can show, I fix it in a second, that this is finite, okay? Well, it's not finite for every sequence, but it's almost truly or in expectation. So we take the expectation over this with respect to, of course, the true distribution, mu, okay? So now what we have here is we have an infinite sum of non-negative quantities, which is finite. And the only way that this is true is that this difference converges to 0. But since there's an expectation in front, this converges to 0 only almost surely. So why does this bound hold, right? And that is Solomonoff's main result, which he proved in 78. And first, we have here, and by the way, this is also not the very exact formulation, but it's actually true in this form. But okay, anyway. So let's take some abbreviation, psi t and mu. So psi t is psi of x t given x less t. I don't want to write this out always. And the same, of course, for mu t. Okay. So what you have here is you have the square distance between psi t and mu t. Okay. You can show it's a version, say, of Pinska's inequality that the square distance is bounded by the KL divergence between mu t and psi t. I give you a more down-to-earth sort of intuition for a finite class in a second, but that's the formal proof. So the square distance is bounded by the KL divergence. So we have a sum over t. I mean, this is super sloppy here and lots of things are missing, so the expectation and so on. So the KL divergence has a telescoping property. So this is the same. So if you sum only up to n, not to infinity, then this is the same as the KL divergence between the x1 to n given psi x1 to n. So I mean, this telescopic property is well known. And if we write this down, then this is sum over mu of x. I really didn't want to go into this detail. ln mu of x1 to n. So let me quick, and then I give you the more intuitive, but that is sort of the proof. So this is this. And if you look at the Bayesian mixture formula above here, so you still have this slide here, the psi was defined as a sum. So if we drop from the sum all terms except mu, so we get mu of x1 to n. Do you see this, what I'm writing?
Mm-hmm, mm-hmm.
Okay. So I just drop all terms except for the true environment. So there's definitely larger equal.
Yep.
So now if I bring w to the left-hand side and psi to the right-hand side, you see that mu divided by c is upper bounded by 1 over w. So this one here is upper bounded by w mu to the minus 1. Okay. Mm-hmm. That's from the above inequality. And this sum, so this is now a constant, and this sum is just summing the probabilities over arbitrary sequences. This just gives you 1. So this bound, and there's a logarithm, don't forget it. So this gives the logarithm w mu to the minus 1. And as long as the prior is larger than 0, then this is, of course, smaller than infinity. Okay.
Sorry, this is
so
a
that's
sum.
The derivation.
I see.
Yeah.
Sorry. N is fixed here, and you're summing over all possible sequences?
Yes, all possible. Yes, that is all possible sequences x1 to n for fixed n. So this shows you that for a fixed n, this is bounded by this constant, but this constant does not depend on n. So now I can let on the left-hand side the n to infinity, because here I started with s infinity. Let's call this s infinity, but then I proved only that Sn, where the sum is up to n. But, since the right-hand side is a constant independent of n, I can just then, once I'm finished, take the limit n to infinity on the left. Okay, let me get to the intuition. So let's assume m is finite and contains m is not used up, m elements, and we choose a uniform prior, w of nu is 1 over m. Okay. What you're doing is, this will be informal now, but you can also formally prove it. So you're mixing uniformly over your environment in the class, and you're making a prediction, and that is very close to a weighted majority, right? I mean, if the majority of distributions want to predict 1, you will predict 1, okay? So let's assume it is a majority voting, which it is not, but it's close. And let's assume the majority is right, predicts the correct thing. Yeah. Then we don't suffer any loss and we are happy. Okay. Let's assume the majority is wrong. We make a wrong prediction. Then we get, in the next time step, we get a feedback. This prediction was wrong. So we can exclude this from the class if it's deterministic hard, if it's probabilistic soft. So this class got halved. So for every prediction error we make, we halve the size of the class. Okay. Once the class is down to just containing one element, namely mu, the true distribution, we are done. Okay. So how many halvings can we have? Well, we can just have at most log 2 m halvings, right? So the number of errors is roughly bounded
I see. So this is the deterministic case where your measure is concentrated on a single, the prefix of a single sequence.
That's the deterministic case.
Yeah. Okay.
Okay. And log 2m is just minus log 2w to the minus 1. So apart from sort of an LL2, you get the same result in the deterministic case with uniform prior and finite clouds.
I see. Okay.
And then you have to make it for non-uniform prior. You get these weights, and it's still the intuition goes through. Then you have to go to stochastic models, and then we don't really use a weighted majority because we use a weighted mixture. So there are differences, but the intuition is the same.
Sure. Okay. Let's just take a step back because so this gives intuition about that bound. But I guess the very high level non-mathematical intuition is essentially let's go back one slide here. What these bounds are saying is that as you make more and more observations, your mixture predictive distribution will converge to the true one. Because for several reasons. One, you assigned non-zero weight to every possible hypothesis, so you don't exclude anything. That was this Epicurus principle that we discussed earlier when doing Bayesian inference. So that's one prerequisite. And the second thing that's happening is, as you just alluded to, as you make more and more observations, the ones that are inconsistent or improbable with respect to mu in general get downweighted, and the things which are more consistent with mu get upweighted. And that happens in such a way that asymptotically you have to converge to mu, your predictive distribution.
Intuitively exactly right. We can even write it down like before. So let me write it down here. So we can write down this psi of xt given history as what I wanted to not do anymore, but let's do it anyway, as nu the posterior w of nu given x less t, and then times nu of xt.
So you use the Bayesian update rule to compute those revised w's, those weights. And what you'll find is that those weights go up for the things which are consistent with mu, and those weights go down for the things which are inconsistent or improper.
Exactly. And in very simple cases, this posterior would just on the true distribution, it would converge to 1, and all the wrong distribution, it would converge to 0.
That's right.
In this more complicated setting, maybe there are two distributions which are totally consistent, right?
That's right.
They can always, but the total weight on the distributions which are consistent with the data converges to 1, and those which are inconsistent converges to 0. That means effectively, in the simple case where there is a single distribution where it concentrates to the true distribution mu, this sum just collapses and gives you mu of xt given x less t. But proving this via the posterior in the general case is hell, and this we will not talk about it.
So, okay, what's next?
Okay. Next, let me instantiate that. That was now. Before we started, it was simple model class like a biased coin. Now we have a completely general framework. We can plug in any model class we want, and we have this bound, right? So let's instantiate it with 2 or 3 interesting classes, which are important because they are bigger, so more interesting, but still tractable, so it can be computed in a fast way.
Okay, so you're going to look at now interesting M's, this family of
interesting
hypotheses.
M's.
Okay, yep, okay.
And I have shown you this bound on the last slide. If we have, and that holds for any countable class, but if we have a continuous class, right, back to it, and again, the proof is hard, and I don't want to do that. If you have a continuous class with d parameters, so let's assume M sort of is a class nu theta, where theta is, say, a d-dimensional parameter. Okay, now. okay? And then you can show a similar bound. There you have to make some smoothness assumptions, but you can show a similar bound, and the bound is then ln w of theta to the minus 1 as before. But now this is a density. Then, because it's a density, you have d half ln n term, and this grows with ln n, so this dominates, so this constant could be avoided. And then you have the logarithm of the square root of the determinant of this mysterious Fisher information matrix plus terms small o of n which converge to 0. Don't worry about all this. The dominant term is this one here, and we just ignore this one. This is a constant, this is a constant. So it's just d half ln n, so the rest you can forget about it, okay, if you have a continuous class. And in the Bernoulli theta case, d was 1, and the bound would be 1/2 log n. Okay, and the intuition is, if you have a continuous parameter, you could discretize this parameter and just take. So we know that we can estimate a parameter to accuracy 1 over square root of n, yeah, and to encode a parameter to 1 over square root of n accuracy, you need 1/2 log n bits, right? So that is one way of interpreting this bound. So each parameter gets discretized to the accuracy which is needed and no more. And then this gives you, we haven't talked about code length yet, but we will get to that. So if you view it the second time, you will understand what I mean with this. Anyway, just trust me. So this is the bound. So for instance, a more interesting class than IID would be a k-order Markov model, okay? So that means that the probability of xn plus 1 depends on xn minus k plus 1 up to n. So the last k parameters, okay? So how many parameters are they, right? For each context here, so assume alphabet size is x, or bar x, right? So context length k, so the k, x to the power of k possible conditions, right? And then we predict xn plus 1, and well, you know, this could be, you know, out of x, but they have one probability constraint, so that is x minus 1 parameter. So in a binary case, it would be 1 parameter. If you have a ternary case, it would be 2 parameters and so on. So that's the number of real-valued parameters you have in this model class. So our D is this one here. Works as before. We just take the bound, you plug this slightly larger D in there, and that's the number of prediction errors you make, roughly speaking. Okay? Nice class, k-order Markov. But if k is large, you see it's exponential in k, and it's no good. So there is a class which I think everyone should have heard about, but many machine learners.
Sorry, are you making the point that in this generalized bound you had above with D and log n, that D is the for the kth order Markov chain? That's the D that you use. This formula that you wrote.
Yes.
Okay.
Yes.
Okay.
Yeah. Because that's the number of parameters I need to specify a k-order Markov problem.
That's right. That's right. Mm-hmm, mm-hmm, mm-hmm.
Okay. Okay. So there's a k-order Markov process. But now I talk about very briefly something context tree weighting algorithm. Okay. So what this
maybe be very brief.
is,
okay.
Yeah. So what this does is very briefly. But we need it later if we come to the approximations. So what is this? Essentially a variable order Markov process. So what you're doing is now instead of using, say, 2 last symbols, you use maybe if the last bit was 0, you maybe need another bit to differentiate it, whether it's 0, 1. But if the last bit is 1, you're fine. You don't need to see further bits in the past. Okay. So you look at these trees, and these trees have, of course, parameters, right? I mean, sort of if the context is 0, 0, you have a parameter. If the context is 1, 0, you have a parameter, and if the context is 1, is a parameter. You also have a number of parameters, okay? So for a fixed tree, you do the same as before. And what you get is, well, D is just the number of parameters. Let's call that the set theta is the set of your parameters, and then it's just the size of this parameter set. Okay, nothing changes. Okay, for a fixed tree. But if you don't know the tree, what we would like to do a Bayesian mixture now over all possible trees, right? Maybe of maximal depth D or so. Okay, so we just take the class of trees. So T is trees of depth smaller or equal than D. Okay, then we need a prior over trees. We can do that somehow, so you can encode a tree in bits and take 2 to the minus the code length. We will get back to that later in a more general context. Tree as your prior over trees. You have, of course, you have the prior over the parameters, where you take your either uniform distribution or the KT one, which we discussed before. And then you do this huge Bayesian mixture over everything. So that the sum over all trees of depth at mod T, the sum over all, once you fix a tree, over all the parameters which are in the tree. And then you have your distribution, which is then the some distribution x1 to n given the t and the theta. Well, the sum over theta is, of course, an integral of a sum. And then you get your distribution, whatever you would call it, it's TTW distribution.
Okay, so is this where this beautiful fact comes in that, okay, if you were to do a naive Bayesian update, you have to update, this, I don't know, double exponential count of weights, because that's how many trees there are. But if you only care about updating the predictive distribution, there's a very nice algorithm.
Actually, it is you can update the predictive distribution efficiently too, but it's much easier to update the joint distribution and then take the ratio. So even the joint distribution is easy to calculate if you calculate it in an online way. And let me just write it down because it's so easy. So yeah, if you would do that, I mean, the integral is easy to do, which is just lots of local little Laplace rule. But the sum is hell, as you said. This class T is about 2 to the 2 to. Okay, so now let's go to larger classes. And before we do that, we have to introduce Kolmogorov complexity, but I can do that very briefly. We don't need much about it. Okay, so generally, let's step a little bit back. In science, we need a principle which is called Occam's razor principle. So if you have two hypotheses which are equally good, describe your data, you should choose the simpler one. And there is no way around it. Sort of without Occam's razor, there would be no science. Believe it or not. Well, it's argued in my book and in many of my papers, so no time for that here. Okay, but what does simple mean? We have to need a quantitative notion of simplicity, and we want one which is, for AGI purposes, which is universal, right? Which is not sort of limited to some, nice classes or something like this. And Kolmogorov complexity does that for you. So think about any object. You code it naively as a binary string. I mean, think about now all data are binary anyway, right? And you ask, what is the information content in this string? Well, if it's a string of all ones, right, it's pretty boring, right? But if it's, pi, it's a little bit more interesting, but it's a very easy description. If it's a picture from a camera, there's a lot of information in there. And we can capture this by how difficult is it to describe my data? Well, we need a description length. Well, let's just take a programming language as a description length, anyone, C or Lisp or whatever you want. Or abstractly, we take a universal Turing machine because, that is also a universal description language. And we look for descriptions of our data. Okay, so let's take this universal Turing machine or your Lisp or your C compiler, whatever you prefer. We look for a program which, if you run it, gives us our string x1 to n. Okay, but there are, of course, many programs which produce a string. For the digits of pi, I can just write print quotation mark 1 billion digits of pi quotation mark. It's a very long program, but there are also shorter programs. And we want to Occam's razor asks for the shortest program hypothesis theory model of our data. So look at the length of the program and find the shortest one. Okay? And the length of the shortest program is called the Kolmogorov complexity of X. And that's it. Okay? And, I don't want to argue here why this is a good measure. You can read it elsewhere. Okay? And we're going to use that. What you can show is that it is nearly independent of the choice of the universal Turing machine. So if you take code with respect to one Turing machine, or you compare it to K prime with respect to a different Turing machine, and you take the supremum over all strings, this is bounded by a finite constant. So if you have strings which are longer and longer, so even over all n, so if you have longer and longer strings, still the difference is just a constant, which is the typical compiler constant between compiling from, say, U to U prime, or from Lisp to C, and so on. And I mean, our data is so much richer and larger in AGI than this compiler constant that you can ignore this problem. Second problem is the incomputability. What you do now there is, okay, this is looking for the shortest program, which looks like compression, okay? So if we have data and we create a self-extracting archive, which means it's a compressed version, but it always also has the decompressor built in. What is a self-extracting archive? Well, a self-extracting archive is a program, if I run it, reproduces my data. Yeah. So what I can do is I can replace the Kolmogorov complexity by, the best self-extracting, the shortest self-extracting archive, which I currently, can create with practical compressors as an approximation. Okay. And how do we use this? Why do we care about this here? Well, it quantifies Occam's data, which is really great. So that it was for strings. If I have any other object like numbers, I can encode it in strings, right? If I have a probability distribution which is computable, right? There's a program which computes it, and I just take this program. So any object O can be coded as a bit string. And then the Kolmogorov complexity of an object O is just defined as the sort of some canonical encoding of it, and you just drop it. Okay. Yeah, so because I will now
maybe just one time. Yeah, I mean, I guess we're always working over countable things, which is why this is possible, because of course there's only countable number of strings and Turing machines. So of course, like when we were talking about probability distributions, by restricting to probabilities over finite length strings, then we're in a countable situation.
Yes, for probability distributions, we only look for computable probability distributions now, right? That means, by definition, there exists a program. That means there's only countably many, okay? And then we write K of nu for a computable probability distribution, and that's used mu for the class of computable probability distributions, okay? Technically, it's lower semi-computable semi-distributions, but let's not go into that. Okay, so now we have a measure of complexity of a distribution, and Occam's razor tells us take the simplest one, but Epicurus' principle tells us keep the all, and we can unify these two principles and say, well, have a higher prior belief in the simple ones and a lower one in the more complex ones, and the same with the posterior. So don't rule out any. So we choose a prior now. Before it was left unspecified. Now we choose a prior, which is 2 to the minus the Kolmogorov complexity of nu. And so that is monotone increasing what you want, and you choose 2 to the minus k of nu because you want it to sum to 1, or at least to be bounded by 1, and you can prove that this is the case, because a prior needs to sum to 1, right? Or at least not more than 1. So we now have fixed, let's call it W nu. We have fixed the class to be all computable probability measures. And for the expert, please forgive me that I'm a little bit crude here with some things. And we have fixed the prior. Well, and we can use Solomonoff's bound for this. So the Solomonoff bound was as infinity was bounded by, so let's plug in this. So we get the xi over this class, let's call it xi u. And the bound was the logarithm w to the minus 1. And if you plug in this is just k of nu times ln2. So this is now actually Solomonov's boundary. This is what he's proven. Okay. And
yeah, no, this is nice because this is saying basically, simpler hypotheses have fewer mistakes on average, right?
Exactly. And even more precisely, if you have a hypothesis, a model, which you can encode, specify in 500 bits, then roughly speaking, Solomonoff induction makes 500 prediction errors, and then it's good. You never can tell where. They could be at the beginning, they could be dispersed out, but you roughly only make 500 prediction errors, and then it's good. I mean, the real result is that you get closer and closer, you get proof sort of the number of epsilon errors is bounded by k of nu divided by epsilon square and blah, 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 and so on. Right? But roughly speaking, and that is also intuitive, right? If I have an unknown world, which I need 500 bits to specify, I need to learn this 500 bits somehow by trial and error, right? So I need to make 500 mistakes. And you can indeed show that it's the best possible bound.
I think what's good to emphasize, because I don't think I appreciated this the first time, is that there are many priors you can write, because the only condition on being a prior is just that each W nu is positive, right? You want to assign positive weight to any candidate hypothesis, and the bound you wrote a few slides ago could have been any such. We could have used any prior, and the C that we had was the mixture obtained from that prior. What's special about the prior that you just wrote here using the Kolmogorov complexity is the fact that it has this sharpness with respect to this bound that I want you to maybe explain a little bit. What's the optimality for this?
Yeah. So what you can show is that this W U of nu, yeah. So you take any other prior over nu, it's computable. I mean, the non-computable priors, I mean, we cannot deal with anyway. Okay, we can take any computable prior. What you can show is that apart from a multiplicative constant, this W U of nu is larger, which means that apart from this constant, minus log, right, is smaller. So if I take now log W nu, the minus 1, then this is smaller than log P of nu to the minus 1 apart from an additive constant. Because the log makes a multiplicative constant, additive constant. And these constants float around anyway. In Kolmogorov complex, you always have to deal with compiler.
Sure.
So apart from this constant, this gives you the best possible bound.
Sorry, what is this lower bound you wrote up to a constant? What's the statement?
The statement is that if you choose any other computable prior,
I see.
It will be smaller than the universal prior apart from a constant.
Okay. Because if it's computable, this is an intuition. I don't know if it's correct, but if it's computable, then you have to use a program that's basically lower bounded by the Kolmogorov complexity, and then 2 to the minus that is smaller, right?
Yes, that's the proof, right?
Okay. All right. I see. Okay. This makes sense. Okay. I see.
Okay. So it is. If your data is sampled from any computable distribution, and let me rephrase, it can be the digits of pi, it can be a piecewise non-stationary sequence, it can be a chaotic sequence or whatever, as long as there is a program of B bits which computes even stochastically, right, your sequence, Solomonoff will learn it in the minimal number of errors.
This makes total sense now. This is very beautiful. Yeah.
Okay, so this was a little bit heavy, maybe. There is a different represent. So this is called this Xi U. This is called the Xi U here. Xi U is the universal distribution. But Solomonoff derived a different distribution, but which turns out magically, which is equivalent. And this different one is, I mean, we had a lot of machinery now going on, right? And, Bayes, and then, Kolmogorov complexity and all this kind of stuff. There's a shortcut to get to this. And I would like to present this shortcut in a short way. So what you're doing here is
let's just pause. This psi u is the Solomonoff prior, right?
That's the Solomonoff a priori. There's two different definitions and versions, and this is one
That's
of
right.
them.
That's right. Okay.
Yeah.
Okay.
Usually I attribute the other one more to Solomonoff, but sort of he came up with both in a sense.
Okay.
So, so the other one is you take a universal Turing machine, and which has an input tape and an output tape. And by the way, I'm skipping over so many things. You need monotone machines and so on. So, but this is all precisely in my new book. We have an input tape, and we sample a uniform random noise, so fair coin flip, on the input tape. Okay. So this Turing machine sometimes will do something, sometimes nothing. So there will be a probability distribution on the output tape. Okay. And let's just call this distribution M of X, whatever that is. But there is a probability distribution of output tape. Okay. And it turns out that M of X is the same as psi of X. Again, you can be more precise, either within a multiplicative constant or for every M there exists a universal Turing machine, so that psi u is equal. So I have a whole paper about this, but essentially it's the same. I will not prove it here. The proof is, long and difficult. I give you a little bit more formal definition of this. What does it mean actually? So we're looking, the input tape is bits, but they are sort of programs. You can ask the question in a second. So this P is input bits, okay, on the Turing machine. And we then run the Turing machine, okay, on P, and then it outputs something. If it doesn't output x1 to n, we don't care. We only look about programs which output x1 to n, okay? So assume there's one program which outputs x1 to n, and only one. Because this program has length L of P, the probability of sampling this program from fair coin flips is just 2 to the minus L of P, right? Okay, but there will be many programs which output X. So we have to sum over all of these programs to get this output probability. So this is exactly the same as sampling infinite random noise and piping it through a universal Turing machine. This is sort of the formal definition here. And then these programs don't need to hold. The star indicates that the programs don't need to hold it. That is fine. And and you can show highly non-trivial that these are equivalent. And that is really nice. So here we only consider deterministic programs predicting strings and mixing over them with a prior, which is 2 to the minus L of P. But the intuition, roughly speaking, is that these stochastic environments are sort of living in the convex hull of the deterministic ones, so are implicitly already included in the deterministic. So you only need to mix over the corners of this infinite simplex in order also to get the middle one. But I mean, this intuition is an intuition, but strictly speaking, it's not right. Okay. But anyway, but the statement is correct.
So we define Solomonoff prior, the Solomonoff mixture distribution in terms of Kolmogorov complexity. You gave this alternative definition. What Solomonoff induction essentially is, it's the Bayesian sequence prediction when we start off with the Solomonoff prior, right? And it has optimal theoretical guarantees. That's what's nice about the Solomonoff prior. Okay. So why don't you describe the two other things you wanted to discuss in this section?
So this is all, good. I covered small model classes, and then this Solomonoff class, which is, incomputable, so you can really use it in practice. Neural networks are all the rage these days, and large language models. What they're doing is, when you're training them, you're minimizing log loss, right? Okay. So if your data set, which is a long string, okay, you have this language model P, which is parameterized by these weights, right? And you predict the next symbol given the history. Of course, they have a finite context, so it's not the whole history, but that's fine. Okay. And training means minimizing log loss. So you take the log loss with minus, right? And minimize over theta. And the argument gives you then, the optimal one. Of course, you do it with gradient descent. You may not get the global minimum and so on, but that's what you're doing. Okay. So, but this is the same as maximum likelihood, right? I mean, you put the minus away and without the log. So this is the same as the maximum over theta, p theta from x. Sorry. You sum here, of course, over all time steps. I mean, you train on the first token, and you train on all the tokens, right? Up to n. You pull the sum into the log, which gives you a product, and the product of the conditional distribution gives you the joint distribution. So that's the same as taking the likelihood function and maximizing this. Okay, so minimizing log loss in LLMs. So maybe I should have an heading here. Is the same as maximum likelihood estimation. Okay, and we know that, I mean, for simple model classes, of course, these model classes are not simple, but if the model class were simple, argmax, that would converge to the true parameter, assuming, of course, that your true parameters in the model class, so that is the class, the LLM class, right? That the LLM can represent it. Okay. I mean, that is really, lots of assumptions here, lots of shortcuts very quick. Okay. So if you would do that, so you have some sequence, say, Bernoulli 1/3, you train your model on a Bernoulli 1/3 sequence, then you stop training, and then you use it for prediction. If everything goes well, it would then predict, Bernoulli 1/3, right? But this view is maybe not the most appropriate one, because these models are trained on a lot of data, right? And there's a chunk of maybe fair coin flips, and then there's a chunk which contains the digits of pi. So more plausibly, actually, our data set looks like x1 to n, and then we chop it up. So you have multiple data sets. And, the first one is maybe, as I said, below half. The next one is a Wikipedia page and so on. So that's more realistic. Okay. So how can we model this? So let's assume that, so these correspond maybe to some parameters theta k, right? But let's assume, let's assume that this k, don't talk about theta, yeah? This k is itself sampled from some prior distribution. Let's call it W of k or something like this. Okay. So maybe I have to put a dot here, right? Some prior. Okay. So you view the real world data as, okay, first I pick a website and then I train on this website, right? And then I pick another website. And this website, one website could be pure noise, the other website is Wikipedia, the third one is a program, and so on. Okay, so that's a better view of the data. Okay, what does it mean? Sampling k, and okay, and these ones, these x1 to nk is sampled from the distribution, say nu k. Okay, so what does it mean first sampling k?
Sorry, and then W is the weights of, like, you could think of these. I'm thinking of these cases like indexing different documents, right? And W is the weight of different documents.
Maybe it would just be a uniform distribution in this case.
Okay, yeah. Okay, and then nu of k. Oh, I see. Nu of k is the language model of language within that document, essentially.
Yes, I mean it could be, in this case it could be deterministic, right? Just the content of this website, right? Or it could be sort of, if it's a agglomerate, if you take sort of k to index over, okay, here all Wikipedia pages, here all Twitter pages, here all programs, then it would be sort of real distribution. But if you find more, it would be deterministic. It doesn't really matter at this level.
Sure. Okay, so, okay. Yeah.
The point is, you sample k somehow, and then you sample x from nu k. So that's an approximate model of where our data comes from. Okay. So what does it mean is, okay, what distribution do we get out? So we take the nu k. Now, first we take the k, but we take it with probability wk. And then we sample our x from nu k. So the probability of actually getting, well, actually, if k is discrete, it's a sum. is something like this. It's a mixture distribution, right? Yeah. So the whole worldwide web data is better represented as a mixture over different distributions, right?
Sure.
Okay. So that is our training. So the distribution or data is, roughly speaking, sampled from something like Xi, okay? Rather than a p theta. I mean, from a very abstract level, there's no difference. But that means if we train on this data, the language model, if it has the capacity to represent Xi, will then learn Xi, okay? And if we then use it for prediction, it will be a Xi predictor, okay?
Sure.
But Xi is a mixture. Right. So that means, for instance, if we take the Bernoulli theta class, we give the model, we sample a Bernoulli 1/2 sequence train, then we sample a Bernoulli 0.8 sequence, then we sample a Bernoulli 0.1 sequence, and we sample. What the language model should converge to, it should converge to the Bayesian mixture over this, which is Laplace rule. And it does. So we tested this, and it perfectly does it, okay? Which is pretty amazing.
I see. I mean, okay, that makes a lot of sense in the Bernoulli case. Just to make this more concrete, in the linguistic setting, this would be something like, okay, suppose for simplicity, you have two domains. You have children's stories and academic articles. And basically, as you sample more and more tokens, if it's really from a children's story, then the prediction should be more and more children's story-like. And if it's more of a scientific article, it should be more and more scientific article-like, right? That's just the linguistic way of reformulating what you just said in the Bernoulli case, right?
Exactly. And we tested it beyond Bernoulli. Yeah, we didn't test it for language because everything is muddled.
Right.
But we used piecewise IID data, which is a little bit more difficult than IID, also works.
Okay.
Then we used this CTW distribution, this highly sophisticated distribution, which I introduced before. And the model also perfectly mimics the CTW distribution in context. This is pretty. So first it was even better than the CTW, which theoretically cannot be the case, but then we found some bugs, some inconsistency, how we train and how we do the inference. So we fixed the bugs, and then it was equal performance, but it was really funny. So this paper is out there, so people can read about it. And then we got ambitious. I mean, then we thought, okay, what we really would like to do is to predict the Solomonoff distribution, but it's incomputable. Let's assume we can sample from this distribution, train a large language model on data which is sampled from Solomonoff's distribution, and if everything goes right, then the model would be able to, in context, emulate Solomonoff's distribution, which is the perfect predictor for everything.
Okay, sure. Actually, just one thing. I'm trying to think what could have gone wrong, because why is this significant? And it sounds like to me what could have gone wrong is that the mixture does not update in the way you expect it. So it could have been rigidly 50-50 with this domain or that domain, no matter how large the context is, right? And I mean, that's a very specific way it could go wrong. Yeah, that's one way it could go wrong. Yeah.
Yeah, but I mean, the way it would technically go wrong is that transformers just don't have the capacity to represent these mixtures, right? The assumption is always that the theta zeros in the class, and that a Bernoulli theta for a fixed theta is in the class is very plausible because it's just IID. The Laplace rule is in the class, counting the number of ones and counting zeros. Yeah, I mean, this should be able to, but they are not so good at counting, and also the context is finite, but it still works, yeah. But these more complex classes, it is a priori not at all clear that the architecture of a transformer is rich enough to represent even this mixture distribution.
Oh, I see what you're saying. Okay.
Not to speak of that the training method gets you there.
Okay. Although language is a very complicated, I guess, in some sense, potentially unbounded or no fixed order Markov process, right? So since it can represent language well, maybe, I don't know okay, it could represent other things, but okay, anyways, just some off the cuff thoughts. Okay.
Anyway, so we got ambitious and thought, wow, that would be amazing, but of course we cannot even sample from Solomonoff's distribution. Um, but we did, we looked at some tiny programming language where short programs already output some interesting strings, and you sample from it, then they train the language. And, we get some positive results. It's very hard to tell, is it great or is it just good, or is it's more than just random garbage. So it does something, and we are happy with the result. But for these smaller model classes up to the CTW and the PTW, it was perfect. And with the Solomonoff, it also does something reasonable. So, maybe, this is a way to go to, basically, we don't need any data, right? So all this is artificial data. It's all trained on artificial data. And then the model does all the actual learning from the real data in context, which is at the moment very fashionable anyway. People, extend the context to millions and try to push everything into the context. I'm not so sure whether this is really the way to go.
Maybe just to clarify, I think maybe one way to say what I was trying to, or a better way of saying what I was trying to say earlier is, so you, going back to the slide, you train your transformer on this data, and you want it to emulate the mixture distribution, which is this psi right here. And one way to evaluate how well it learned it is precisely to generate longer samples and see that the rate at which it converges to the true mu, it obeys the right properties, right?
Yeah, that would be one to evaluate, but in this case, we could also just, at least for the CTW and the Bernoulli, we could directly compare the distribution to the mixture because we have the mixture, right? The practical evaluation is always against the truth, of course, right?
Of course, yes.
But the scientific evaluation, we could just evaluate against xi itself.
Oh, I see, right. You could just compute the probabilities directly from the model outputs and compare it to the mu in this case. Yeah, fair enough.
Okay, so we're nearly done with the prediction part, but sort of as a bridge to the agent part, let's consider loss functions and sort of actions, but let's still call them predictions because there's a major difference between the agent case and the prediction case. But the loss function still sort of can fit in here. So loss functions. So the protocol is similar to before. We make a prediction, but let's call this prediction now YT. Okay. Then we observe XT. Okay. Then we suffer loss XT, YT. Okay. The important point is that we do not see XT before we do the prediction. Okay. And in general, I call it prediction, but this could be in any other space. So if XT is in X, YT could already be in a different space Y. And so, for instance, say you do weather forecasting, but you can say, if it's rainy, I take my umbrella, and if it's sunny, I take my sunglasses, something like this. So the prediction or action is actually taking umbrella or taking sunglasses. So they live in different spaces of different sizes even. So that's all already included. The important point is that your prediction or action, whatever you want to call it, does not influence the environment. Still not. Okay. So your action taking umbrella, or sunglasses doesn't affect the future weather. We know there's a butterfly effect, but we are assuming that there's the butterfly. Okay. So if you do this, then the best we can do is, so we have the loss we suffer, but we don't know XT. Okay. So let's just take the expectation over XT. So the history is fixed. With respect to, well, ideally the true distribution, but let's take some distribution. Okay. So that's the expectation only over XT. And then we want to minimize this loss. T. Okay. And let's call this the rho predictor. Okay, so the row predictor minimizes row expected loss. Now it's standard setup, nothing special. So what is the real loss I suffer with the strategy? Well, the real loss is, well, whatever the outcome is, okay, whatever the outcome is, but the outcome is, of course, uncertain. The true xt is sampled from my true environment, distribution mu. Mu is always the true environment, okay? So this is my true expected loss if I use strategy YT row.
Okay. So expectation with respect to S above, that's with respect to your own model of the sequences, not the true one?
Well, above it was the expectation with respect to some row, not specified at the moment.
Oh, okay, I see, okay.
But this is not the true expected loss. True expected loss, I have to take the expectation with respect to the truth, right?
Sure,
so
okay.
I use the row expected predictor, but evaluate it with respect to the truth, of course.
That's right. Yes,
okay?
Yes. Mm-hmm.
So now I take also the expectation over the history. So I just take the expectation here. Now I sum over all time instances. Let's sum to n. Yeah, I probably don't need really I can't use infinity. Okay.
So to use your weather analogy, the row could be like how to best choose your weather prediction, say in the United States, and then maybe now you live in London, and then mu is the London distribution of weather, right? So sort of you could incur loss because of the mismatch, for example.
Yeah.
Great.
For instance.
Yes.
Yeah. Okay.
Great. Mm-hmm.
So let's call it loss of. So loss of row is the total loss, lifetime loss, expected loss with respect to the true distribution for the row predictor. Okay. Obviously, by construction, if I would minimize with respect to the true distribution, that is the optimal thing to do, right? This is smaller than the loss of row, right?
Yes, of course.
So if I minimize with respect to the criterion, right, then of course this is better than doing anything else. Okay, that's fine. But again, as before, we do not know mu, so we have to do something else, right? And you could be a machine learner and learn mu somehow, or you're a Bayesian, you just replace mu by a Bayesian mixture psi. Okay? So, loss mu is the best you could ever achieve if you know mu. And let's look if we use psi. So we minimize the psi expected loss and compare these two losses. Okay. And now I have to do a little bit of a funny trick. I take the square root here and the square root here, because otherwise I can get a bound, but it's ugly. So I just don't compare the losses, but the square root of the losses. Okay. Just the difference is called the Hellinger loss. Okay. No, I don't need to take any square. Okay. And ask, well, if this is bounded by a constant, for instance, then I would know if the optimal mu loss is finite, then the optimal psi loss is finite, which is great, right? Remember, it's over infinitely many steps. If the loss of mu sort of has a certain frequency, maybe 50% or something, then the psi loss also has the same frequency, assuming there's a finite bound. And the amazing thing is there is a finite bound. This finite bound, as usual, is the ln w of mu to the -1, now with a square root.
Is there, how do I say?
And for the specific case of Solomonoff's distribution, right?
Is this loss like, I'm surprised it should be even finite in the first place, right? So it's sort of like, if you have for example, if your loss is 0, 1 accuracy, then this loss function will generically have an infinite sum over ones, right? Is there some discounting? Maybe I'm not understanding.
It's different. Assume you want to predict. Say, assume the weather is Bernoulli 0.7 or something like this. Okay. Yeah. And
Okay, sorry, keep going. Yep.
And you have a loss function, and you choose your umbrella, your sunglasses. Of course, you often get it wrong, right? So you will suffer a loss, right? Which actually, so I need the n because that's infinity, right? So I need
exactly. That's the point I was trying to make. Yes.
I need up to n, and then this is n, and this is n. But then I can but then I can take the limit n to infinity on the left-hand side.
Sorry.
Not the n root.
Yeah, okay, thank you.
N. N. I wasn't quite sure with that.
Yeah, essentially this is like a regret bound, essentially, right?
Yes, except that there's a weird square.
Yeah, sure, exactly. Yeah. Okay, right. Yeah.
But you can convert it over. But this is the best way to see it, in the simplest way and the fastest way. That's a very, very, very neat bound. Okay, so that shows, I should have, this bound holds if the loss function is in 0, 1. So it must be a bounded loss function. Any bounded loss function, you just scale it, but if it's unbounded, it's more complicated.
Okay, so not cross entropy. Okay, yeah, sure, something like that, yeah. Okay.
So the nice thing is that Solomonoff prediction is also optimal in this sense with respect to any loss function you care about, not just the square distance between the distributions or the log loss or something like this.
So just to maybe make one remark, because of the optimality that we discussed earlier, which is that if you have any computable measure, then you're going to assign less weight up to constants than the Solomonoff weight, which is 2 to the minus Kolmogorov complexity. Then this upper bound becomes larger because of this log of a reciprocal, right? So in this sense, the Solomonoff prior gives you the best convergence rate and also the optimal regret, right? Which is the minimal regret, right? So this is amazing. This is great. Yeah.
It is.
Okay.
So let's end with a nice, or maybe we can start the next section. Or you can cut it if you like. So let's end or start with a nice quote of Marvin Minsky. When he was quite old, 2011, and he never worked on Kolmogorov complexity or Solomonoff induction, but there was a panel discussion with him and Gregory Chardin and some others, and it was 1.5 hours. And the last statement, this whole conversation by Marvin Minsky was, and I'm paraphrasing, I don't know exactly, but pretty much, Solomonoff's theory is a beautiful theory about prediction. Everyone should know everything about this theory and spend the rest of their lives working on it.
Wow. Okay. Okay. Noted. So why don't we now start on part 2 of our outline. Let's just maybe quickly recap what we've done. Part 1 was called Universal Prediction, and we explained how, well, there's the Bayesian setup, which tells you how to do prediction once you update your priors to get posteriors that are now data informed, data revised. We introduced Kolmogorov complexity, so we could talk about the Solomonoff mixture distribution or Solomonoff prior, however you want to call it. And that gave us a prior that had optimal convergence properties, both with respect to prediction and loss. And then we also discussed some interesting model classes. But what we've left out is action planning, right? Because at the end of the day, intelligence requires interacting with the world. Those actions will influence the world. And so we want sort of the action version of this. And that's where the universal artificial intelligence comes in. And this is where your contribution comes in, right? So is that a fair summary of where we are?
Yes, I mean, my contributions, apart from Solomonoff's original bound, everything else I told was also sort of a lot of my contributions. And there's much more I have done. There's this paper, a philosophical treatise of universal induction. There are so many other bounds and interesting insights you can have, right, where unfortunately there's never time to get to this. This paper in a lightweight form, and there's an older paper in a more heavyweight form, contains sort of a summary of all the other stuff related to Solomonoff induction itself. Yeah, but the major contribution is indeed to the active agent case.
Yeah, I should say, of course, your books will be a proper monograph giving citations and references, so people who want to know more about the contribution histories can refer to that. But okay, great. So maybe should we just get started in section 2? Yeah, we're pretty open-ended. I guess basically we want to adapt, how to say, kind of technically my sense is we've done a lot of the work. The planning part is sort of, at least at a high level, a modification of that, in that, okay, now you just add this action part, and you can talk about kind of the same theorems they carry over, and now it's a matter of reinterpreting it. Of course, there's many other downstream consequences of that, but at a high level, I think we've done most of the technical conceptual work, and now it's sort of shoehorning in the action part, and you can ask the same questions, right?
Yeah, you can ask the same questions, but you don't get the same answers.
Okay.
The active case is much more complicated and much more tricky. I mean, apart from the base optimal notion, which is sort of an optimal notion, which is, I would say, good by definition, or I mean, from the foundational derivation of probability in Bayes, it's very difficult to come up with notions of optimality in the agent case, which are on the one hand strong enough to be convincing, but on the other hand weak enough so that real agents can actually satisfy them. So that even the right notion of optimality is still open, I would say. Unlike in the prediction case where you just use regret or redundancy and sort of you don't have to compromise much there. Anyway, okay, let's start with the agents. And for a second, let us forget about Solomonoff and all this kinds of stuff, but start very simple. Let's assume we know the world, right? What's happening, okay? So the setup is the following. I mean, it's a typical agent environment setup, and soon the rewards come in. I draw the picture a little bit different from the standard way because, standard RL is usually, MVP based, and that is too limiting for AGI agents, right? We want something, at least when we start, something which is, general. That means general history-based environments and policies. And so the picture I usually draw is you have an agent, and you have an environment, and they interact with each other. And the agent, as well as the environment, they can remember stuff arbitrarily long in the past. So let's sort of put this sort of on a tape. Yeah. So there's a sequence of perceptions. So E's are perceptions. That was the X before. The agent can have. Okay. And once it has a perception, it can act somehow.
Is perception the same as observation?
No.
Okay.
You will see in a second.
Okay.
So, and the agent then acts somehow, and it, this action can depend on the whole history of perceptions up to time step 3, and then the environment gets and can remember all the past actions of the agent if it wants to, and then produces a new percept. So that's the reason why it connects to E4. So that's the next time step. It produces a new percept, and then the cycle continues. So formally, what we have is we have an agent, which we call, the behavior of the agent is called a policy, right? Which takes, and here in this picture, it looks like that the agent only depends on the perceptions, but the agent can also remember its own actions. I don't need to because it produces the actions, rather because it knows its own actions. So the policy with a mapping of past actions and perceptions up to the star means like 1, 2, 3, 4, 5, and produces a new action. And the environment is also having access to the whole history of actions and perceptions and the last action of the agent, and then comes with a new perception. And since the policy and environment can be stochastic, I just write this as a wiggly arrow. Wiggly means it can be a stochastic metric. I mean, sort of you cross a part 2, 0, 1 or something like this. Okay. So, and this interaction produces an action observation or action perception sequence. So ET is sampled from nu of ET given, and now I use this glue notation A sometimes disappears here, A is less than T, and the last action of the agent, AE. So AE is sort of glued together. So it's action 1, perception 1, action 2, perception 2 up to T minus 1. And the actions are sampled from the policy, or the deterministic policy is just, deterministic output, action given the action perception history, right? Okay, you start at T equal 1, there's no conditions, and you generate them sort of, based on the...
So this is AE tuple, like all the pairs of AE up to less than T, right?
Yeah,
exactly. Just to emphasize, so maybe just...
So the joint distribution, so we can do that. So if we take, we start at T equal 1, and the first thing is the agent's action. So it produces an action with a certain probability. So T is equal 1, so there's no history, it's just the first action. Then the environment reacts to this action. And then, T equal 2 starts, T equal 3 up to, say, T equals, say, assume the agent dies at times that M. So for simplicity, I just assume that the agent has a very long horizon M, say, lives for 100 years and then dies, right? So, but you can also be infinite horizon, but then you need discounting for the rewards and so on. And infinities is always a little bit annoying. So I keep it simple here. So this is a joint distribution which generates the action perception sequence up to M, which we denote by nu pi. Okay? Maybe I should add this of E1 to M. So that's the probability of this action perception, EA. AE. AE1 to M. So that's the probability of the action perception sequence if environment nu, if agent pi interacts with environment nu. Okay? So now we ask, what does the agent do, right? And we wanted to do well with respect to some criterion. And in reinforcement learning, you have the reward signal. So we split the perception into an observation and a reward. Yeah. So the perception is observation reward pairs. Yeah.
Okay.
O2, R2, and so on. So when I write E, it's always with pair OR. Okay. And the goal of the agent should be to maximize its total reward over its lifetime up to M. But these rewards are, are stochastic, right? Definitely the environment. Either the environment is itself stochastic or later we have a belief over the environments. So this reward sequence happens with a certain probability, right? And what's the probability? Well, the probability is nu pi, right? But the policy pi we want to choose, right? We only care about the stochasticity of the environment. So the probability of observing a certain perception sequence given a certain action sequence, actually, I come to that later. Let's keep it simple. So this produces this reward sequence, but with some certain probability. So let's take the expectation. So the expectation is with respect to the environment nu and with respect to the policy pi. Okay. And this expected reward sum is called the value of agent pi in environment nu.
Sorry, I think your R's and your nus look similar. That's an expectation of rewards. Is that right?
In the squares is R's.
Okay.
Is a nu. Sorry. Okay,
yeah,
I'll try to be.
Yeah, your R's and nus. Okay, all right.
Well, I think what they have. Anyway.
Okay. Anyways. Okay.
So that's the value of agent pi in environment mu. Okay. If we know the true environment.
Okay. By the way, and are you absorbing the discount factor into the rewards then?
No discounting here because it dies at horizon m.
I see. Okay.
Yeah, I could do discounting, and then I can take the limit m to infinity, and all the versions exist, and they're also more useful. So by not doing that, and there's also, you don't want geometric discounting because for any gamma you choose corresponds to an effective horizon, which is 1 divided by 1 minus gamma. So if you choose gamma 0.99, it corresponds to an effective horizon 100. But there are problems which need larger horizon. If you choose gamma 0.999, it's horizon 1000. But there are problems which need higher horizon. But there are discount schemes which are not geometric, which generate agents with a growing horizon, for instance, proportional to the age of the agent. Which makes a lot of sense, right? But I don't want to go into this. So if we know the true environment, then the agent's pi's true expected reward sum, so the true value is V pi mu. And, well, we want to maximize this, right?
So mu is the true environment, and nu is the...
Mu is some environment. Got
it. Okay, yes.
Okay, let's put it to row so that it's easier to read. Okay, and this, let's call it pi star. Okay, but so that would be the optimal policy, right? If we knew in which environment we are. Okay. Okay, but, well, we don't know mu, so what do we do? Yeah, okay, we learn mu. How do we learn mu as a Bayesian? What could we do?
Well, Bayesian updating.
Yeah, Bayesian updating, which means if in the predictive formulation, you just replace it by psi, the mixture distribution.
Sure. Yeah, exactly. And then as you make more observations, you'll get convergence.
Exactly. Okay. So now let's define also pi star Bayesian mixture. Well, the Bayesian mixture is pretty much obvious. I mean, everything is now conditioned on action. So, I mean, I could write it down, psi of x1 to m. So E1 to m given actions A1 to m is equal to, well, nu E1 to m given A1. So there's some subtlety. This is not the real conditional probability, but I use a double bar. So here is sort of, remember at the beginning I said there's a difference between conditioning and indexing. So that is actually indexing on A. And here it makes difference. Some people have spent a lot of time and figuring out what is going on here. I mean, in one sense it's trivial. In another sense, it's really subtle. What I call them chronological semi-measures. Say chronological probability distributions which satisfy the causality constraints. But again, we don't have to go into it. It's in some sense it is obvious. Okay, so now this pi star, that is what we want, pi star mu, but we cannot have it because we don't know mu. So we use this policy pi star psi, okay, which I call AI psi. It's not the AIXI model yet, but we are close. Okay, so and now we want to compare the performance of this Bayesian agent to the agent which knows the world. Okay, so how can we do that? Well, we look at the value, but this psi value is just sort of a tool for creating a policy. This has no meaning, right? I mean, not direct. What we really receive is the mu value. Okay, so but we act with a psi optimal policy. Okay. So we ask, what is the true mu expected reward sum if we act with a psi policy? And we compare this to the optimal mu agent. Okay. This optimal agent, of course, has smaller value than any other policy by construction because it's just the argmin. But what is this relation between the base agent and the optimal informed agent? And well, in the predictive setting, we proved this loss bound, so Solomonoff bound, and so on. And in the active setting, under certain extra conditions, you can also prove asymptotically that they converge to each other on average. You can prove so-called self-optimizing results. You can prove asymptotic optimality results. There's weak optimality, strong optimality, optimality in Cesaro sense. There's lots of different optimality notions, but they all come with conditions under which this holds, so they're not condition-free.
By the way, I think you meant lower bound. We're trying to maximize reward here, right? Argmax. Sorry.
Oh, yes. Yeah. So this is approximately the same in a certain sense under certain conditions. Conditions on M. I mean, for instance, this framework is general enough that if you choose a class of environments M, which do not depend on the action, so if I cut this arrow here from the action tape to the environment, so in the diagram, so if the nu respects this, so it does not depend on the action, so here I may have made an error if it does not depend on the actions, then we are back in the passive prediction setting. And for instance, for this class of models, right, we get the Solomonoff bound back. Yeah, but we get also bound beyond this class, of course, otherwise it would be boring. Okay, so finally, that is nice, but we have to choose a class. And from an AGI perspective, right, we want the class to be, I mean, from a technical perspective, we want it to be as small as possible to deal with it practically. But from an AGI perspective, we want to do it big enough so the true world is in the class. And I mean, if you look at physical theories, standard model, generativity and whatever, they're all sort of computable theories. I mean, very hard to compute, but they are computable. So again, if you take the class of computable probability distributions, you should be pretty safe that the true world is in the class. Yeah. So again, so we choose M to be MU, which is all computable. In this case, lower semi-computable chronological semi-measures, if you want to be precise. Yeah, but roughly speaking, all computable probability use mu. And as prior, as before, we choose 2 to the minus the Kolmogorov complexity of mu. Then you get a psi, which is psi u, and this is called the AIXI model. Okay, and now if you think even intuitively about what this model does, it combines universal sequence prediction, which we have shown to be optimal, with optimal decision making in known environments when it's also optimal, and combining these in these two ways by just plugging Solomonoff into the sequential decision theory framework sounds like an optimal decision maker in arbitrary unknown worlds. And if you parse this sentence, this feels like AGI. And you can also define an intelligence measure out of this. So you can regard V psi pi, that is the performance of policy pi averaged over all environment in the class with a certain prior. And you can call this, for instance, the intelligence of an agent pi. And Jane Legg, my first PhD student and co-founder of DeepMind, wrote a whole PhD thesis just about this intelligence measure.
So pi is a policy, psi is this Kolmogorov, the Solomonoff mixture prior, right? And you're calling this value function the intelligence.
Yes,
can you write down
intelligence of agent pi, so epsilon of pi, because I mean this is I mean we can write it out explicitly by linearity. This is just the sum over all values in all environments over the class times.
Oh, I see. It's sort of like measuring its fitness with respect to general environments. Is that how to interpret it?
Yeah.
Okay.
Yes. So it measures the average fitness over these environments, averaged with a sort of what comes prior.
I see. Let's take this down to earth a little bit, because we're working in the countable space of all computable programs. In practice, right, we never do have this infinite space where we have to juggle all these quantities. In practice, there is some finite subset of discourse, of consideration. And I'm wondering to what extent, if you choose a large enough finite set, sort of this becomes, let's say, applicable, tractable, meaningful, right?
Yeah, but that is probably a little bit too naive. This finite set needs to be really large, right? So assume you can describe our universe in 100 bits, right? 100 bits is not very much, right? So, but assume you can describe in 100 bits, right? There are 2 to the power of 100 programs of up to 100 bits, right? So that is already a class of size 2 to the power of 100. It doesn't really help you. So
I see.
Unless you can do the mixture more efficiently than naively, like in the CDW case.
I see. Yeah. So basically, as soon as
it becomes computable, but practically not.
That's right. Very large finite numbers are basically out of reach very quickly in this business.
Yeah. Anyway, so that's all good. Let me briefly. That looks very abstract. Let me give you another formulation of this agent, which is much easier to grasp what is actually going on. Here we're doing an argmax over policies, and policies are functions from high-dimensional spaces. There's a different way to writing this bow down. Avoiding all base and mixture and all this kind of stuff. Let's first again start with the true distribution, mu of E1 to M given action sequence, and again. This is not really the conditional distribution, okay? So that's just the perception sequence, assuming that a certain action sequence is done, okay? So M is where the agent dies. We don't care about the last perception. That just wait a second. The goal is, of course, to maximize reward sum, okay? But the last perception we don't care about. So let's just take it out. And what that means is that we just take the expectation over the last perception. So now we have the last action, and then the world ends, right? Or the agent ends. So what do we want to do? Well, we want the action to maximize reward. So we take the action, which maximizes this reward sum. Okay. So that's in the last. So we're going from back, right? From the last day or last second of the agent. And so now, how did we get there? Well, the environment produced a perception En minus 1. And before the agent receives the perception, we don't know it. So let's take the expectation with respect to E minus 1. Okay. And now we take the action at time M minus 1, which maximizes the expected future reward. So that it.
You're for those who know, you're basically unrolling the Bellman optimality condition, right?
Yes. Yeah.
Okay.
And the Bellman equations are really only useful if you have a Markov process, right? Because then you really have this self-consistency. But because it's history-based, you can write it down in a Bellman form, but it's not really recursive, because at every recursion step you have a different length history. So you don't really gain.
Okay, yeah. If this were the MDP, but you're basically you're unrolling the tree, right? And you're just working backwards. Yeah.
Yeah. Okay. So and then of course we go up to assume we are currently at time step k. So we sum over the ek and we take the maximum at time step k, and then the optimal action is just the argmax. Okay. Mm-hmm. So. And you can write it down in a tree, right? If you look it in the tree representation.
Right. Basically you decide, right, once you decide what the optimal move is at a node, then you can analyze the optimal move from the parent, because the parent, you have the reward for each action, and then the value of all the of the child, which encapsulates all the decisions below it, and so you just kind of recursively work your way up, right?
Exactly. And so if it were a classical minimax game, right, you would maximize your value when you have actions, and the environment would minimize the actions, so then you would have a minimax tree. Mm-hmm. But here the environment is not necessarily adversarial, it's stochastic. So instead of a minimax tree, you have an expectimax tree.
Yeah,
so
that's right.
That's right. Why you have these expectations here.
Right.
So these sums are the expectations.
Yeah.
Okay. So that is the expectimax. max 3. Okay, so far so good. This is if we know the environment. And by the way, we can specify, assume we play chess, so we could define an environment mu, which is in this case deterministic, which is adversarial, which means it would only put probability on one particular, from the environment's perspective, action, from the agent's perspective, observation, namely the optimal action. Then all these sums would collapse to picking out the minimizing element, and the expecting max would reduce to minimax. So if mu is the chess environment with an optimal opponent, then this would reduce to minimax. So I just want to say it includes also minimax of zero.
Right, because I think what you're saying is that if you play against the strongest possible opponent, there's no margin for error. So they're always going to choose the thing which is minimizes your reward, which maximizes the adversary's reward. So everything concentrates on the best moves, and it becomes, that's right. Mm-hmm.
Okay, so far so good, but that's with respect to the true environment, right? What if we don't know the truth? Okay, now the pattern repeats. What do? We replace the mixture, right?
Yeah.
So I could just write psi here, and we would be done. But let's be a little bit more explicit. So remember, in the prediction case, there were two formulations of this psi. One was in terms of Bayesian mixtures, and the other one was just piping random noise through a universal Turing machine, which was much easier in a certain sense. So we can do the same here. Nothing much changes. So we look for programs P which output perceptions E1 to M. But now, need some space. We have actions as conditions, right? So the universal Turing machine also has the actions available, okay? And we look for a program which, given the actions of the agent, and produces the observation sequence, so explains the observation sequence relative to what the agent has done. Okay, so and we weigh each program by its probability, and the probability of a program should be 1/2 to the number of bits. So we weigh each program by 2 to the minus L of P, and there are many programs which output this observation sequence, so we sum over them. So in this formulation, you look for all deterministic world models P, which are consistent with the observations E1 to M. But it also depends what the agent does, right? If I look left, then I see the perception is different than if I look right. So everything is dependent on the actions. That's the reason why the action will also function of you.
And sorry, was there a reason we went back to the deterministic case? That I assume this all works in the indeterministic.
Because to write it down explicitly, I mean, can write psi, and then we can look up psi and so on. But now what we have here is, if I circle this here, apart from the definition of a universal Turing machine, which is sort of not trivial, right? Everything is completely explicitly in here. There's nothing, there's an action space site and observation space site, which you have to specify. But otherwise, everything is here written down explicitly. Nothing is hidden. I mean, that's the only reason to write it out like this. I mean, how do you enumerate all computable probability distributions? Yes, you can enumerate all functions, and then you can, top these functions towards the problem. So, I mean, there's a long process to really get to this Bayesian mixture distribution. But here, this is trivial, right? So you just write it down in, 20 characters. That's the only reason. It's equivalent. I can just write psi.
Okay, sure. Sure.
Okay, so that's this AIXI agent. And I guess we can move on from this. I would like to talk about some variations of this model, which has advantages and disadvantages. So given that it's very hard to prove convergence results, alternatives have been developed.
Let's
go back to the original formulation where we had where we took let's maybe this formulation. We had the psi value, one representation, what we represent as a new value, times its prior, and then sum over all new in the class. So that was the psi value. And then we argmaxed it to get the optimal policy. Okay. So here we look for the performance to maximize the performance averaged over the environment.
Mm-hmm.
Okay. What we could also try to do, we could do a minimax. Instead of this, we could do the minimum over all new, maybe still weighted, right, over new, and then argmax it.
I see. The first line is just linearity of expectation, right?
The first line is linearity of expectations, yes.
Yep, okay.
So if we replace the sum by a minimum with or without this weight, that would be trying to perform best in the worst possible worlds, right? We look for the new, which gives me minimal value, and I want to perform well in this. That would be sort of a minimax strategy.
Okay.
Interestingly, if you have prediction problems, that can work under certain circumstances well, usually of finite classes or compact classes and so on. But for the active agent case, that is actually a bad idea. Very interestingly, if you replace the minimum by a maximum, so it's a maximax principle. So you look for the best possible world and you want to act well there. You can show that at least for finite classes, you get an asymptotically optimal agent. And then you can extend it to countable classes with some tricks of making the class growing. You can extend it to compact classes. I mean, compact classes always you fill it with finite degree epsilon balls. Then you can extend it to separable classes, this result. So anyway.
So this is, I mean, this is saying like you should be, under these assumptions, you should be an optimist, not a pessimist, right? You act as though the world is in your favor. And if you try to optimize that situation, you'll do the best, versus the other way around, where I'm going to act in a way such that I assume the world is most against my favor, right?
Yes, and you can explain it in two ways. So we know as soon as we go to the active setting, we need exploration. And being optimistic encourages exploration. So if there is an environment where we, look, this is all still Bayesian, so we don't know much about it. So if we believe it could be good, right? Then we try it. And either it is good, then it was a good action, or it's not good, then we have learned a lesson. And then based on the posterior, it will go down. So the optimism gives you exploration.
Okay. Was there something else?
So this is the optimistic agent. The optimistic.
Yes. You said there were two things, right? Optimism is exploration. Was there something else?
So it encourages exploration, and and also, I mean, if you are optimistic and then you act, which I said, either you were right, then everything is good, or you were not right, then you learned a lesson. And this sort of useful.
Okay. This is a bit of a philosophical tangent, but I think where this makes a sharp contrast with reality is that, two things. One, we as mortal human beings, positive and negative rewards are highly asymmetric, right? Death is like a negative infinite reward. And in some sense, positive reward is bounded because there's only so much, money or, diminishing returns, right? And then in practice, people do have a, concave reward utility function for precisely that reason, right? We're much more risk averse, and so we're usually more pessimistic in some sense than optimistic Anyways, maybe this is too much of a philosophical tangent, but that is something that, why aren't we more optimistic? Because I think our situation differs from the assumptions of whatever this agent is, by what I just said.
The assumptions are here that the rewards are bounded in the interval 0, 1, or at least sort of in a bounded interval. Mm-hmm. In my old book, I have a whole section about how to deal with concave loss functions and how to reduce this and so on. Yeah, we could spend a whole...
Sure, okay.
But let's not do that.
Of course, I just, yeah.
So, and also, this is not naive optimism. You have to update with the posterior, right? It is a
realist. It's an
a realistic optimist. Yeah.
Yes, that's right.
Okay. Because you take the feedback into account, right?
Exactly.
The posterior, the environment, which were inconsistent with what you were hoping for.
That's right. Yeah, that's right.
Okay. In a very tiny setting, the UCB algorithm, upper confidence bound for bandit problems, right? Mm-hmm, that's a similar. It's similar, right? You're optimistic with the arms, and either you were right or not. Then you learn something, and that you still respect your posterior belief in the environments. Okay, so that was the optimistic agent. Another agent is Thompson sampling agent, for which that is one agent for which you can actually prove without any real restrictions asymptotic optimality, at least for some form of asymptotic optimality. And what you will there is, so now, I said...
Okay, so to summarize, we took the ideas from part 1 about universal prediction, added in action, and the optimality conditions now become optimality conditions on things like regret and learning the environment. What you just outlined here were sort of, sorry, let me start before I jump to that. And you could even furthermore write an explicit formula for what AIXI is. These variants that you wrote down were sort of different ways of trying to learn the environment by using other sort of strategies, let's say.
The learning of the environment was the same. The learning is always our base rule.
Okay.
How to choose the actions was a little bit different.
Sorry.
I choose the base optimal action, the Thompson sampling choose as well the Thompson sampling action, and then the knowledge-seeking agent sort of is exactly AIXI, but chooses a reward function for you.
Mm-hmm. They're different. Yeah, I guess these are like kind of different policy learning methods, essentially. Is that a way of phrasing it?
Yes, Thompson sampling and AIXI sort of is different ways of follows different. You have to distinguish between updating the posterior belief and what you do with this belief, right? How to act according to this belief, right? Sure. And so Thompson sampling and AIXI are sort of different choices, and the knowledge-seeking agent solves a different problem, namely where do the rewards come from, and self-AIXI tries to avoid the expected unexplained.
Okay. Anyways, okay. So I think let's just leave it at that as the summary. So I guess we have some time maybe just to say just a few odd things here and there as we choose. I know you wanted to talk about the grain of truth problem. Maybe that's just one last thing we could put in. Maybe close with some philosophical discussions. We already had a few, but maybe anything that you'd like to. Kind of like final thoughts about the subject, essentially.
Yeah. Okay, that's true. That's the multi-agent setting. Yes. So far, we have only considered one agent, but since the framework was so general that the environment could be anything, there could be, of course, other agents too. Yeah. But there is more to say than this. Okay. So let's first draw a picture, but I don't need to say too much of it. It's extremely sophisticated. The final result, what I want to present, the grain of truth problem was a problem which was open for 25 years, and then some of my students solved this. So you have now multiple agents, which each have their own policy. So they assume you have K agents, and the policy is pi 1 up to pi k, and they act with an environment now. So there's an index up there. So the agent 1 acts with AT1 at time t, and then perceives ET1 up to the last agent. So APK, and perception is ETK. So pretty natural, and of course it also goes in cycles. Okay. So what we could do is we could just look at the first agent and regard all this here, right, as an environment, right? This first agent, it acts and it perceives, and that this environment itself sort of consists of k minus 1 extra agents. We can ignore that to some extent, right? So let's call this class M.
By the way, are the agents always acting in succession, cyclic order always, or is that an irrelevant detail?
That's irrelevant for our description. Yeah, Okay. I mean, technically it becomes important, but for here it doesn't matter. They're acting in parallel. Okay, like in game theory, they have parallel actions, so on. But let's not go into this.
Okay.
So let's start. So I started a little bit different. Before we looked at I never specified a policy class because we just looked at all policies and then the best among all policies. So let's start with some policy class pi. Okay. Some potentially restricted class. Okay. And let's also assume that all these agents, have some policy in the policy class, not necessarily the same policy. Okay. And so once we have given the policy class and assume there's also an environment class sigma, but let's assume there's just one environment, doesn't really matter, right? There's also a class of environment sigma. We can construct then by, gluing these k minus 1 agents to this environment sigma and can create a traditional one agent environment out of it. Okay. And we do that for all possible combinations of policies in this policy class. And this generates a class, let's call this M capital pi. Maybe I should make a double bar so you see that's a capital pi. So that's this class M pi. Okay, so here we start with policies and create our single agent environment class M pi. Now we have M pi. The next thing is we construct our xi, the base mixture over this class as before, and now it is called say xi, again it's invisible, M index pi. Okay, it gets lots of indices. Okay. Now we have the base mixture distribution. The next thing we want to construct optimal policy with respect to this base mixture, like the AIXI model. Okay.
So just to get this straight, so you're trying to reduce this multi-agent formalism to the previous formalism where there was a single agent. So it almost sounds like to do that, you need agent 1 to act alternatingly with the other agents, right? So it's sort of like action and percepts, right? Is that an assumption?
The action and the perception is alternating, but all the actions are parallel.
Okay.
Anyway, let's not go into it. I can spend at least 50 hours on this if you want.
Okay, sure, okay. So let's continue. Okay.
So now we look at the value of a policy. So of policy pi 1, I should call it, right? In this Bayesian mixture over this class we have just constructed. Okay. And what we want is, we want the optimal agents. So we take the argmax, and that is our pi 1 star.
So hold on, let's see. Let me think about this. I see. So M pi is the universe of policies we're going to consider. The C is the whatever I don't know, what do you call it now? The Solomonoff mixture, the AIXI mixture. What's the name of the
base mixture? Just call it base mixture.
Actually, but you are using it's any base mixture. But I thought you were using
at the moment I'm not using any specific Solomonoff class or Solomonoff.
Oh, I see. It's any base mixture. Okay, sorry. Okay, C is a general base mixture. Okay, that's what I was trying to understand. Okay, I see. Okay. Please continue. Yeah.
Yeah. So xi index M always means the mixture with respect to the class M, whatever M is.
Well, yeah, right. I see. Well, I see M is the set and also the weights. Then I guess. Okay. Yeah. Okay.
Okay. So we go from a class of policies to a class for a single agent environment. Then we construct the base mixture, and then we construct the optimal policy with respect to this base mixture. Okay. So now, so far, all good. But now comes the real question. We started with a class of policies, and via this loop, we constructed a new policy, pi1 star. So is this policy actually in the class or not? If it is not in the class, then it would mean that if we want these agents to be base optimal agents, then they are not in the class. But we started out with a class assuming that these policies are in the class, so we have a problem. So what we need is, we need pi1 star to be in the class pi itself.
Sorry, what is the obstacle? Because if you're considering the class of all whatever computable, semi-computable, blah blah blah, how could it not be? You want a smaller class? Is that what it is?
Well, if you start with a class of semi-computable distributions, then the psi is also semi-computable, but the policy pi psi is not lower semi-computable anymore. It is only limit computable. So it is one step further removed from computability.
I see. I see. We didn't. In the previous setup with that was not multi-agent. I guess we didn't care where pi star lived. Now we do.
Exactly.
Okay.
Yeah. Okay. So that is called the grain of truth problem. Grain of truth. And the question is.
Sorry, can you explain the naming of that?
I guess it comes from you want the true environment in the class, but it needs to be. It can be a very big class, and just one environment needs to be in there, and I think this is the grain of truth.
Okay. Sorry, please continue.
Yeah. So that was by Carly and Bempala, 1993 or so. So they formulated this problem, and maybe in this paper or in another paper, they or somebody constructed a tiny, super boring class where this grain of truth is true. I mean, it's more or less sort of an environment where you have a fixed action and then you die or something like this. I can't remember. I mean, it's definitely not AGI. It's not even a bandit. Nobody else could ever find any class, non-trivial class, where this grain of truth holds. And so that was this big open problem. And one of my students, Jan Leike, and some Miri guys actually before that, they found a class which is relatively, so the Miri guys constructed a class which it was not even sure whether the distributions in this class are in the arithmetic hierarchy. So this is something, I mean, really crazy. I mean, sort of again, just leave it like that. But Jan Leike then showed it that it's actually in delta 2, so it's limit computable, which is sort of the realm where Solomonoff works anyway. So this class is not the class of lower semi-computable semi-distributions, but it's a class of all reflective oracle computable measures. And this construction is hell. Okay, let's not go into this. So we have, as a result, we have a class M, which contains all computable distribution, such that pi1 star is in pi. So contains a grain of truth. So the important thing is it contains the computable ones, which we want. And another important thing is not too big. It is at least a subset of delta to 0. It's not so crazy, which is really great because the reason why we care about to be this put in the class, that means the condition that psi is in the class is now satisfied. Yes. So the psi is itself in the model class, or the pi psi more precisely in the model class itself. Therefore, the conditions which you usually need for most of the Bayesian theorems, most of the Bayesian theorems, if the true class is in the model, then good things will happen, right? And so this condition is now satisfied, and we can apply the previous theorems, and especially the one for the Thompson sampling agent. If we now do Thompson sampling in this multi-agent setting, we get an asymptotically optimal agent, which in this case means they converge to Nash equilibria in this ultra general, model class, which is I mean, from a theoretical perspective, it's a highlight of also the book. Then this result.
Okay, wow. I think there's a lot to unpack here, but I think, at this point, only the experts are here. I think we could end with just two more things. I did say philosophical discussions, but maybe another important topic, maybe if you could just say a little bit about it, are computable approximations, because everything we've done now is sort of very abstract, and maybe, how would you modify this for real life?
Yeah, so actually it's sort of, I mean, to the extent that we have done it, it is easy to explain. So the first approximation we did is we just used for M the class of Markov environments. Actually, K-order Markov environments. Was it K-order? Yes, I think K-order Markov environments. And for the K-order Markov environments, you can easily, I mean, the mixture over the parameters theta gives you, KT estimators. And then we used only binary actions, the observation spaces. And then the expectimax, if it's binary tree, you can roll it out to depth 8, which means 16, 2 to the 16, sort of these days, sort of much more. And then we considered these small 2x2 matrix games like Prisoner's Dilemma, tit for tat, playing against trivial strategies, random strategies, against tit for tat. There are games like Prisoner's Dilemma and Matching Pennies and Battle of the Sexes and Stag Hunt and the Chicken and so on. So there are 5 sort of standard games, and did some experiments, and the outcome was more or less like expected. I mean, these are now AIXI approximations. So if you play one stronger approximation against the weaker one, the stronger one wins. Sometimes they cooperate against sufficiently simple strategies like tit for tat. If it's too complicated, they don't cooperate. So more or less sort of it worked as expected. Next, more complicated approximation was then using the CTW. Remember?
Sorry, let's pause here. Sorry. So now the AIXI setup worked for general computable environments. A computable approximation is when you say, sorry, let's back up. There's the true environment, and then there's the class of environments you're going to use to approximate the true environment. And mu might not be in M, of course, that's going to be most of real life, right? And so you're seeing how well can you do in this sort of misspecified setting, right? Yes,
I mean, if for instance, we let AIXI play against tit for tat. Tit for tat is one Markov strategy, which is in the class, right? Mm-hmm. Then the theory should hold. But if we play against, a more complicated environment, especially if we play against itself, right? Then we are outside of the class, theory breaks down, and we have to just see empirically what happens.
Mm-hmm. Although, I'm trying to think if, what do I say? What I want to say is, I see. You only have a a binary alphabet or some fixed alphabet. Okay, I was going to say I guess
binary, very small alphabet.
Yeah,
because they pretty much as expected.
Yeah. Otherwise, if you allowed unbounded alphabet, then I guess you could include board games where you have a very large state space of possible boards, but obviously with binary, you're not in that situation.
Yeah.
Yeah. Okay. Anyways, yep.
Okay, so that was the first very simple approximation. Then with the MC AIXI CTW. There, what we did there is we used the CTW distribution, right, which is much more powerful, but still very fast to compute. But now for larger either observation action sequences or for non-binary, you cannot just do the expectimax brute force. But there's an algorithm called Monte Carlo tree search, which we just adapted to our case. And we deployed it to, which asymptotically for enough samples converges still to the exact expectimax. But of course, I mean, in practice, you're never close. But, it is nice to have an algorithm which at least, is an anytime algorithm is running long enough, sort of you get to the truth. So it still has, also these theoretical guarantees in these certain limits. And we applied it to a lot of toy problems like grid worlds and the most sophisticated, a very trivial form of poker called cool poker. And then we ran it on Pac-Man. Well, we call it POC-Man, partial observable Pac-Man. And for all the toy worlds, including cool poker, this approximation learned to play optimally, asymptotically. And for Pac-Man, we also saw performance improvements, but I mean, of course, it didn't converge to optimal. So that was a more sophisticated approximation. For
these situations, what's the observation is whatever, like in Pac-Man, it's the screen, right? There's some n by n grid.
But we do POC-Man, where the agent only observed in the four directions. I can't remember exactly anymore whether it was up until a wall or up until some object or ghost or something was there, and then the distance or so, or maybe just one cell. So it was from a first person's perspective what the agent can see. Which made the observation space smaller, so it was more easier to handle in this case. I remember that was way before the Atari paper from DeepMind. And by the way, this approximation was by Joel Venez, who then also worked on the Atari problem. So it evolved from MC AIXI CTW playing Pac-Man toward the Atari suite.
Okay. Okay, great. So is that?
Let us briefly talk about the LLMs, right? So I showed you the connection before, how these LLMs trained on log loss are essentially trying to approximate Solomonoff, right? But that's the prediction part. How is the action part? Okay. If you look at the action part, well, I mean, people use foundation models also for agents. And maybe the closest would be mu0, right? Where you take a learned model and then do planning on top of it. So instead of approximating Solomonoff by CTW, you could just approximate it by a large language model and then do Monte Carlo tree search on top of it. There are other ways, like, there's chain of thought, there's tree of thought, where, you roll out. It's a little bit similar to MCTS, right? You roll out various futures, and then you get a tree, right? And then you decide what to do. So that would be a way to find a connection, right? And sort of mu0 is in a sense closed. It does the Monte Carlo tree search, which approximates expectimax, and it uses mu0 doesn't use a language model, but uses other models. So if you would use a language model and then with mu0 style planning, then you could regard this, as a rather straightforward, I mean, not straightforward, but a rather principled way of approximating the AIXI model.
So in the language model setting, what would be the reward?
You would also have as tokens rewards. There would be some tokens which are sort of related to reward. I mean, if it's discrete, it's just a reward 0 to 10 or something like this.
Sorry. I mean, with like things like RLHF, you can have human raters give a feedback as to whether.
Yeah, I'm not talking. RLHF is sort of barely RL, right? So what you would here have is that the language model itself. So you train. Maybe I shouldn't call it language model, but sequence model or foundation model or whatever. So you are training the model of sequential data, which consists of actions, observations, and rewards.
Oh, okay, I see.
Yeah.
Okay.
And then it also predicts the observations and rewards. And then you just roll it out into the future and select a rollout where the rewards are high, right?
I'm a little confused here. What's the problem you're trying to solve?
I'm trying to extend the current rather simplistic approximations of AIXI to larger model classes. And
I see.
Model classes we now know, and the most predictors we have are currently large language models.
Oh, I see. Got it. Okay. That makes sense.
So you plug into AIXI, instead of Solomonoff, you plug in a language model.
That's right.
Then you still have the expensive expectimax, but this you replace by Monte Carlo tree search like in
Zero. Your C is now your LLM, essentially.
Yeah, exactly.
Yeah. Okay, got it. Okay, makes sense. Sorry. Yeah. Okay, yeah. I was confused with the notion of reward, thinking of RLHF, and okay. Okay, I think we've MC, AIXI, LLM. But this so many letters. It's like this almost looks like all, with the exception of maybe the A, it's all Roman letters. Okay, looks like a bunch of Roman numeral, like you're trying to write a large Roman numeral or something like that. Except for the A. The A throws it away. I don't know what number that is if you threw away the A, but okay. Anyways, too many capital letters. Okay, maybe one final thing as we close up. I know there's a final chapter or two in your book about philosophical aspects. Your book is quite philosophical in the sense that it's not just all, even though there is a lot of math, it ties it wherever there's relevant philosophy, you'll sort of make that correspondence. But you mentioned kind of at the beginning some historical context for the problem of induction. Famously, Hume and his predecessors have sort of, let's say, I don't know the right way to say it, but kind of cast doubt about the validity of induction. And then there's more recent works like the Popper-Miller theorem about maybe various problems with the formalism of induction. To what extent do those perspectives do they inform AIXI or the other way around? What's the relationship between these?
Well, as far as I can tell and remember, Solomonoff was influenced by Carnap's theory of induction, so Carnap's induction theory. And the Carnap theory was essentially, maybe he did more, but was essentially Laplace rule. But Laplace rule has the problem that it cannot confirm universal hypothesis. So if you ask what is the probability of the next bit being 1 given the history, you seem to get a reasonable answer. But if you ask what is the probability that all future will be 1, like, you have seen 100 black ravens,
right?
What is either the probability that all future ravens are black or that the hypothesis all ravens are black is true? If you solve that in the simple base Laplace model, you get probability 0. You don't even get probability, you get 0, which makes no sense, right? So you see 1 billion ravens, black ravens, and then it predicts the probability that all ravens are black is 0, right? So this model fails. And interestingly, at least from the technical literature I am aware of, most quantitative approaches fail on this task of quantifying or predicting so-called universal hypothesis or quantified hypothesis. And although Solomonoff doesn't explicitly sort of consider this problem, I considered it later, Solomonoff solves this problem. In one of my papers, the philosophical treatise of universal induction, I go through a couple of these philosophical questions and show how Solomonoff solves them. There's the problem of zero priors. There is the more technical problem of reparametrization invariance. So this paper looks at a bunch of philosophical and statistical problems which most approaches have, and shows that Solomonoff solves all of them.
Okay, actually, in this very specific case, I think what you're saying is the following. Suppose the observations you made are all ones. You've seen a billion ones. Now there is a program which says, actually, my program is print all ones, and because it has positive weight on that, quite large weight because that's a very simple program, then there is a positive probability that indeed all future digits will be one, right?
Exactly. Yeah, it's as simple as this, right? It is simple example, right? And but interestingly, Laplace rule, Carnap's theory, and most of the other theories I'm aware of get it wrong.
I see. Although maybe it's a little unfair because with Laplace's rule, you're only allowed these Bernoulli predictors, and you're in such a small model class that maybe you. I mean, of course, technically you do have p equals 1 as a limiting point in your hypothesis class, so that you never select for it because you always have to have some margin of uncertainty, right?
I'm not even asking for selecting that p goes to 1. I mean, of course, ultimately we want that. If we see n ones and n tends to infinity, the probability of this hypothesis should go to 1. But I'm just asking that it's not 0.
Exactly. That's right. Yeah, that's right.
Even this most models get wrong.
Okay. I don't know enough about
the prediction part, and from the philosophical perspective, from the decision theoretic perspective. I mean, there is something like causal decision tree and evidential decision tree. There's also some philosophical paradoxes, and the Newcomb's paradox, and you can try to reason how AIXI would sort of deal with these paradoxes. I think these paradoxes are very fun, but they are rather irrelevant from a practical AGI perspective, because I mean that's not, you don't face this Newcomb type problem in practice, right? Because there is no omniscient person who can predict what you're doing and put it into. And if so, you have the differential problem and so on. I discussed that a little bit in one of my papers. But so I would think the deep philosophical aspects are in the induction and prediction part. The sequential decision part is sort of relatively solid.
Okay, I see. Okay. Anyways, okay, I think we've definitely covered a lot. Thank you so much for your time, Marcus. This is a very fascinating subject, and I think, hopefully this will bring it to the attention of more people.